Welcome back, Night Wanderer. Tonight, we're drifting through the solar system, exploring the worlds that orbit our sun, these ancient spheres of rock and gas that have been spinning in the darkness for billions of years. If you enjoyed this journey through the cosmos, consider subscribing to the channel for more peaceful explorations of the universe. Now, let's begin. Think about your day for a moment. The Earth spun you through one complete rotation, sunrise to sunset to sunrise again. 24 hours, give or take. It's a rhythm so fundamental to human experience that we've built our entire lives around it. But out there, on Venus, something strange happens with time itself. A day on Venus is longer than its year. Let that settle in your mind for a moment. One rotation of the planet, one spin on its axis, takes 243 Earth days. But one orbit around the Sun, one complete year, takes only 225 Earth days. Venus celebrates its birthday before it finishes a single day. If you stood on the surface of Venus, assuming you could survive the heat and the crushing pressure and the sulfuric acid clouds, you would experience something profoundly alien. You'd wait through your first Venusian birthday, and then your second, and then your third, and only then would you see the sun complete one journey across the sky from sunrise to sunset. It's a reminder that time itself isn't universal. The way we measure our lives, days, nights, weeks, is entirely local. It's Earth-specific. Out there, in the rest of the solar system, time moves to different rhythms entirely. Mercury is the closest planet to the Sun. It orbits at a distance of only 36 million miles, as compared to Earth's 93 million. During the day, when the Sun hangs directly overhead on Mercury's surface, temperatures climb to 800 degrees Fahrenheit, hot enough to melt lead, hot enough to turn zinc into liquid pools. You'd think Mercury would be uniformly scorched, a dead ball of baked rock with nothing but heat and radiation. But Mercury has ice. Deep in its craters, particularly near the poles, water ice sits frozen in permanent shadows. These craters are deep enough that sunlight never reaches their floors, not in all the billions of years since they formed. In these shadowed places, temperatures plummet to hundreds of degrees below zero. The ice has been there, perhaps, since the solar system was young. Ancient water delivered by comets, trapped in eternal darkness while just over the crater rim, the surface bakes under the unfiltered glare of the sun. It's one of those cosmic ironies. The closest planet to our star, where you might expect everything to be reduced to ash and vapour, harbours reservoirs of ice that have never melted, never evaporated, never seen daylight. Perhaps it's a reminder that even in the most extreme environments, there are pockets of preservation, places where the unexpected survives. Jupiter has a storm. You've probably seen pictures of it. The Great Red Spot, an oval of swirling clouds large enough to swallow 2 or 3 Earths. But here's what makes it truly extraordinary. This storm has been raging for at least 400 years, possibly much longer. 400 years. Think about that time span. When humans first observed the Great Red Spot through early telescopes in the 1600s, it was already there. Already massive, already churning. The entire history of modern science has unfolded beneath this storm. The Industrial Revolution came and went. World wars were fought. Humans learned to fly, split the atom, walked on the moon, sent robots to other planets, and through it all this hurricane on Jupiter just kept spinning. On Earth, our most powerful hurricanes last days, maybe weeks. A month-long storm would be extraordinary. but Jupiter's Great Red Spot has outlasted civilizations. It's a weather system older than the United States, older than the scientific method, older than the concept of nations as we know them. And it's still there, still spinning, still maintaining its shape despite all the forces trying to tear it apart. Maybe it won't last forever. Observations suggest it's been shrinking over the past century, but for now, it endures, a testament to forces we're still trying to fully understand, a storm that has weathered centuries and shows no sign of stopping. Imagine an ocean large enough to hold Saturn. You'd need a body of water hundreds of thousands of miles across, deep beyond comprehension. Now imagine placing Saturn in that ocean. Here's what would happen. It would float. Saturn is the only planet in our solar system less dense than water. Despite being 95 times more massive than Earth, despite being large enough to fit 764 Earths inside it, Saturn is mostly empty space filled with hydrogen and helium, the lightest elements in the universe. If you could calculate Saturn's average density, you'd get about 0.687 grams per cubic centimetre. Water is 1.0. Saturn is lighter than water. It's almost absurd to think about. This massive world, with its spectacular rings and dozens of moons, this giant that dominates its region of space with its gravity, would bob on the surface of an ocean like a cosmic beach ball. Of course, no such ocean exists, and if it did, Saturn would likely dissolve into it or react chemically in spectacular ways. But as a thought experiment, it reveals something profound about the nature of these gas giants. They're not solid in the way we understand solidity. They're more like atmospheres that never end, growing denser and denser as you descend until the gas becomes liquid. Then the liquid becomes something stranger still, but never quite solid, never quite a surface you could stand on. Saturn is a world of gradients, of slow transitions, of matter in states we don't encounter in our everyday lives. Mars is red. You can see it with your naked eye on a clear night, a rusty point of light among the white and blue stars. The Romans named it after their god of war because of that blood-like colour. But the reason for Mars's redness is far less dramatic than warfare. The planet is rusting. The surface of Mars is covered in iron oxide. Rust. Somewhere in Mars's ancient past, iron in the rocks combined with oxygen in the atmosphere, creating the red oxidized minerals that now coat the entire planet. Essentially, Mars is a world-sized example of what happens when you leave metal out in the weather for too long. The entire planet is slowly corroding, painted in the colour of decay and time. But here's what makes it haunting. This rusting happened billions of years ago. The Mars we see today, red and dusty and dead, but is the end result of processes that finished long before Earth had continents, before our planet had anything more complex than single-celled organisms. Mars rusted when the solar system was young, when it still had a thicker atmosphere and possibly liquid water on its surface. Then something changed. The atmosphere thinned, the water disappeared, and Mars was left frozen in time, locked in that rusty state, a monument to its own lost past. When you look at Mars, you're seeing ancient corrosion. You're seeing the stain left behind after a planet died. Neptune is the farthest planet from the Sun in our solar system, orbiting at a distance of about 2.8 billion miles. Out there, sunlight arrives 900 times dimmer than it does on Earth. It's a realm of perpetual twilight, where the sun appears as just a bright star in a black sky. You'd think Neptune would be calm, frozen, almost motionless in that cold darkness. Instead, Neptune has the fastest winds in the solar system. Storms rage across its surface at speeds exceeding 1,200 miles per hour, faster than the speed of sound on Earth. These are supersonic winds, howling in the near darkness, driven by forces we still don't fully understand. On Earth, our weather is powered by the sun. Warm air rises, cold air sinks, and the differential heating creates winds. But Neptune receives almost no solar energy. The winds there must be driven by something else, perhaps heat from the planet's interior, perhaps some mechanism involving Neptune's unusual magnetic field, perhaps something we haven't even theorized yet. We don't know for certain. What we do know is this. In the frozen outer reaches of the solar system, on a world that should be quiet and still, winds rage with unimaginable fury. Neptune is screaming into the void, and has been for billions of years, powered by mysteries we are only beginning to unravel. Uranus rotates on its side. Most planets spin like tops, their axes roughly perpendicular to the plane of their orbit. Earth tilts at 23.5 degrees, which gives us our seasons. Jupiter tilts only 3 degrees, spinning almost perfectly upright. But Uranus has an axial tilt of 98 degrees. It's essentially rolling around the sun like a barrel, its poles pointing at the sun during different parts of its orbit. The leading theory is that early in the solar system's history, Uranus was hit by something massive, perhaps an Earth-sized object, perhaps a series of smaller collisions that knocked it over. This wasn't a glancing blow. It was catastrophic enough to permanently change the planet's orientation, and Uranus has been tumbling sideways ever since. This creates the most extreme seasons in the solar system. Because Uranus takes 84 Earth years to orbit the Sun, each pole experiences 42 years of continuous sunlight, followed by 42 years of complete darkness. Imagine living through a summer that lasts 4 decades, where the sun never sets, circling endlessly around the horizon. Then imagine that summer giving way to a winter of equal length, where the sun never rises and darkness stretches on for your entire adult life. Uranus's sideways rotation is a scar. It's evidence of violence from billions of years ago, frozen into the planet's motion. And every time Uranus completes an orbit, it repeats that ancient trauma, rolling through space in a way no planet should. Earth is the only planet not named after a god. Mercury, Venus, Mars, Jupiter, Saturn, these are Roman deities. Uranus and Neptune continue the tradition with Greek gods. But Earth? Earth comes from the Old English word iord, which simply means ground. The ground beneath your feet. The dirt. The soil. It's fitting in a way. The other planets were named by people looking up at lights in the sky, mysterious wandering stars that seem divine in their movements. They deserved names of gods and goddesses. But Earth was where we lived, where we walked, where we planted crops and built homes. Earth didn't need a mythological name because it wasn't distant or mysterious. It was just here, the ground we stood on. There's something humble about that. While every other world in our solar system bears the name of a deity, gods of war and love, or kings of the heavens, lords of the sea, our planet is simply called the ground. It's a reminder that for most of human history, we didn't see ourselves as living on a planet at all. We were just here, on the ground, under the sky, not fully grasping that the ground itself was a world spinning through space. Perhaps it's a useful kind of humility. This isn't the realm of gods, it's just the ground, and we happen to be standing on it. Jupiter has a moon called Ganymede. It's the largest moon in the entire solar system, bigger than the planet Mercury, bigger than Pluto, bigger than any other satellite orbiting any other planet. Ganymede is 3,273 miles in diameter, large enough that if it orbited the Sun directly instead of orbiting Jupiter, we would classify it as a planet in its own right. But Ganymede is trapped in Jupiter's gravitational well, doomed to be a moon forever, circling the giant planet every 7 days. It's a world in its own right. It has a liquid iron core, it generates its own magnetic field, it may have a subsurface ocean sandwiched between layers of ice. In many ways, Ganymede is more complex than Mercury, more geologically active, more potentially interesting. But because it orbits Jupiter, it's categorized as a moon. It raises an interesting question about how we classify things. Is Ganymede fundamentally different from Mercury just because of what it orbits? They're both rocky bodies, both spherical, both large enough for their own gravity to pull them into round shapes. The only real difference is their location. One orbits the Sun, one orbits a planet. And that arbitrary distinction determines whether we call it a planet or merely a moon. Ganymede doesn't care what we call it. It spins in the darkness around Jupiter, a world unto itself, larger than some planets, complex enough to still hold mysteries we're trying to unravel. Venus has an atmosphere so thick, so dense, that the pressure at its surface equals being 3,000 feet underwater on Earth. If you've ever gone scuba diving, you know that even at 100 feet down the pressure is noticeable. Your ears need to equalize. Your equipment has to account for it. At 3,000 feet, the pressure is crushing, literally. It would compress your body, collapse your lungs, crush any structure not specifically designed to withstand it. That's what standing on Venus would be like. The atmospheric pressure is 92 times that of Earth. The air itself, though it's not really air as we understand it, more like a supercritical fluid of carbon dioxide, would press down on you with the weight of an ocean. And it's not just the pressure. The temperature at the surface reaches 900 degrees Fahrenheit, hot enough to melt lead, maintained uniformly across the entire planet by those thick greenhouse clouds. The Soviet Union sent a series of probes to Venus in the 1970s and 1980s, the Venera missions. Several managed to land and transmit data from the surface. They lasted minutes, sometimes an hour or two at most, before the heat and pressure destroyed them. The longest surviving lander, Venera 13, operated for 127 minutes before falling silent. Just over 2 hours of data from the surface of Venus, bought at the cost of years of engineering and billions of rubles. Venus isn't just hostile, it's actively crushing, melting, corroding everything that touches it. And it's been that way for billions of years. Mountains on Earth are limited by gravity and geology. Mount Everest stands at 29,032 feet above sea level, the highest point on our planet. But Everest is near its maximum possible height. The rock at its base can only support so much weight before it begins to deform, to flow like putty under the pressure. Earth's active plate tectonics also work against mountain building, constantly reshaping the surface, preventing any single peak from growing indefinitely. Mars has no such limitations. Mars has Olympus Mons, a shield volcano that rises 72,000 feet above the surrounding plains, nearly 3 times the height of Everest. It's so tall that its peak pokes above much of Mars's thin atmosphere. And it's so wide that if you stood at its base and looked toward the summit, you wouldn't see the peak at all. The mountain would curve away beyond the horizon. Olympus Mons is 374 miles across, roughly the size of the entire state of Arizona. This volcano grew so large because Mars lacks plate tectonics. On Earth, the crust moves, carrying volcanoes away from their magma sources. The Hawaiian Islands formed this way, a chain of volcanoes created as the Pacific plate slowly moved over a stationary hotspot. But on Mars, the crust doesn't move. A volcano can sit over its magma source for hundreds of millions of years, erupting again and again, building higher and higher, limited only by the strength of the rock beneath it. Olympus Mons is extinct now, or at least dormant. It hasn't erupted in millions of years, but it stands as a monument to geological processes that happened over timescales we can barely comprehend. A mountain built one eruption at a time over hundreds of millions of years. Saturn's rings are one of the most beautiful sights in the solar system. Even through a small telescope, they're breathtaking. Those elegant bands of light circling the planet suspended in space. For a long time, we thought they were solid disks. Then we realized they were made of countless small pieces. Now we know they're mostly water ice, billions upon billions of chunks ranging from tiny grains the size of sugar crystals to house-sized boulders, all orbiting Saturn in an impossibly thin disk. If you could shrink Saturn's rings down to the width of a piece of paper, they would stretch for a mile. Yeah, they're about 175,000 miles across, but only about 30 feet thick in most places. It's one of the flattest structures in the solar system, a disk of ice and rock so thin it's almost two-dimensional, yet so vast it dwarfs our entire planet. The ice catches sunlight and reflects it beautifully, which is why the rings shine so brightly. But here's something to consider as you drift off tonight. Those rings won't last forever. They're being eroded by Saturn's gravity, slowly spiraling inward, raining down onto the planet below. Scientists estimate the rings might only have another 100 million years before they disappear entirely. In cosmic terms, that's soon. That's a blink. We're living in a time when Saturn has rings. It's a temporary state, a moment in the planet's history. Billions of years from now, if anything is around to look, Saturn will be just another gas giant, ringless, less spectacular. We're fortunate to exist when we do, when there's still this much beauty left to see. Beneath your feet right now, thousands of miles down through rock and metal, lies Earth's core. It's impossibly hot down there, about 10,800 degrees Fahrenheit. That's roughly the same temperature as the surface of the Sun. The Sun, that ball of nuclear fusion 93 million miles away, is matched in temperature by the iron core at the center of our planet. We live on a thin shell of cooler rock floating above an interior that rivals a star in heat. The ground beneath you, solid and stable as it seems, is just a crust, a thin skin of solidified minerals, only a few dozen miles thick in most places. Below that is the mantle, hot rock that flows over geological timescales like a very slow liquid. And below that the core, an outer layer of liquid iron and nickel surrounding a solid inner core of almost pure iron. The heat comes from two sources. Some is left over from Earth's formation, when countless smaller objects collided and merged to build our planet. The energy of those impacts converted to heat, and that primordial warmth is still radiating outward, still working its way to the surface after 4.5 billion years. The rest comes from radioactive decay, elements like uranium and thorium slowly breaking down, releasing energy in the process. This internal heat drives everything. It powers plate tectonics, it creates our magnetic field, it causes volcanoes and earthquakes. We live on a dynamic, churning planet, and all that activity is fueled by a core as hot as the sun's surface, buried beneath miles of rock. Jupiter should be cold. It's 5 times farther from the sun than Earth, receiving only about 4% of the sunlight we do. By all rights, it should be a frozen, inert ball of gas, slowly radiating away whatever warmth it once had. But Jupiter emits more heat than it receives from the sun. If you measured all the energy coming from Jupiter, both reflected sunlight and infrared heat, you'd find it's giving off about 1.6 times more energy than it absorbs. Jupiter is still warm from its birth. When the planet formed 4.5 billion years ago, it pulled in gas from the surrounding solar nebula, growing larger and larger until it had accumulated more than 300 times Earth's mass. All that matter falling inward released tremendous amounts of gravitational energy, heating the planet, and Jupiter has been slowly cooling ever since, radiating that ancient warmth into space. But it's not just passive cooling. Jupiter is also shrinking. Very, very slowly, at a rate of about 1 inch per year, the planet is contracting under its own gravity. This gradual compression generates heat through a process discovered by Lord Kelvin in the 1800s. When you compress a gas, it heats up. Jupiter is essentially a cosmic hand warmer, still releasing the energy of its formation billions of years later, supplemented by the heat of its own slow gravitational collapse. In a sense, Jupiter remembers its creation. The warmth radiating from it now is an echo of the solar system's birth, energy that has been trapped inside the planet for eons, slowly leaking out into the cold darkness of space. Neptune wasn't discovered by looking, it was discovered by mathematics. In the early 1800s, astronomers had mapped the orbit of Uranus with increasing precision, and they noticed something odd. Uranus wasn't moving quite as it should. Its orbit showed small deviations from what Newton's laws of gravity predicted. Something was pulling on it, disturbing its path. 2 mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated where that something should be. They used only mathematics, solving complex equations that described how an unseen planet would need to be positioned to create the observed perturbations in Uranus's orbit. Le Verrier sent his calculations to Johann Galle at the Berlin Observatory, and on September the 23rd, 1846, Galle pointed his telescope to the predicted location. Neptune was there, almost exactly where the mathematics said it should be, here within 1 degree of Le Verrier's prediction. It was a triumph of theoretical astronomy, proof that mathematics could reveal truths about the universe even when observation failed. Here was a world billions of miles away, invisible to the naked eye, found not by seeing but by thinking, by following equations to their logical conclusion. It's a beautiful reminder that the universe follows rules, and those rules can be understood. Sometimes you don't need a telescope. Sometimes you just need paper, ink, and the patience to work through the calculations. The universe will give up its secrets if you ask the right questions in the right language. Mercury is small and close to the Sun, whipping around our star at tremendous speed. It completes 1 full orbit in just 88 Earth days, less than 3 months. If you lived on Mercury, you'd celebrate 4 birthdays for everyone you'd celebrate on Earth. The planet moves at about 105,000 miles per hour in its orbit, the fastest of all the planets, racing around the Sun in a blur. This speed is necessary. In orbital mechanics, objects closer to the massive body they orbit must move faster to avoid falling inward. Mercury is so close to the Sun that it needs to maintain that incredible velocity just to stay in orbit. If it slowed down even slightly, the Sun's gravity would pull it inward, sending it spiraling toward destruction. But despite all that speed, despite orbiting so close to the Sun, Mercury takes 59 Earth days to complete one rotation on its axis. So while its year is very short, its day is relatively long. This creates a strange relationship. Mercury rotates exactly 3 times for every 2 orbits it makes. It's called a 3-to-2 spin-orbit resonance, a cosmic clockwork precision that emerged from millions of years of tidal interactions with the Sun. Mercury is locked in a gravitational dance, its motion choreographed by forces that have shaped it since the solar system's formation. It's the fastest planet, the closest to the Sun, racing through its orbit at speeds we can barely comprehend, yet following rules as precise as any timepiece. Mars has seasons, just like Earth. It has spring, summer, autumn, and winter. But because Mars takes about 687 Earth days to orbit the Sun, almost twice as long as Earth's year, each Martian season lasts roughly twice as long as ours. A Martian spring stretches for about 7 months. Summer lingers for over half an Earth year. Autumn is a slow fade lasting months. Winter settles in and stays. Imagine experiencing that. Imagine a spring that lasted from January to August, flowers blooming and temperatures slowly rising for more than half a calendar year. Or a winter that began in November and didn't end until June, snow and cold extending through what would normally be multiple seasons. Our experience of time would change. The rhythm of the year would feel elongated, stretched out, each phase of the seasonal cycle given room to develop fully. Mars also has a more pronounced seasonal variation because its orbit is more elliptical than Earth's. When Mars is closest to the Sun, it's about 26 million miles closer than when it's farthest away. This difference in distance affects how much sunlight Mars receives, making some seasons warmer and others colder beyond what the axial tilt alone would create. Under salmon-coloured skies, Mars's atmosphere scatters light differently than Earth's, making the sky appear pinkish red. These long seasons unfold. Dust storms rise and fall. Carbon dioxide freezes out of the atmosphere at the poles in winter and sublimes back into gas in summer. And the seasons march on, slow and patient, measured in a time frame twice as long as ours. If you could somehow hover above the solar system and look down from above the Sun's north pole, you'd notice something remarkable. All the planets orbit in roughly the same plane. They're not scattered randomly in 3-dimensional space. They're arranged in a flat disk, like a spinning record. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, all of them circling the Sun in nearly the same plane with only slight inclinations. This arrangement isn't a coincidence, it's a memory. About 4.6 billion years ago, the solar system didn't exist as we know it. There was only a cloud of gas and dust, slowly rotating, slowly collapsing under its own gravity. As it collapsed, it began to spin faster. Conservation of angular momentum. This same principle that makes an ice skater spin faster when they pull their arms in. And as it spun, it flattened, forming a disk with the proto-sun at the center. The planets formed from that disk condensing out of the gas and dust, growing from tiny grains into planetesimals into full-fledged worlds. And because they all formed from the same rotating disk, they all inherited that disk's rotation. They all orbit in the same direction, in roughly the same plane, preserving the memory of the cloud's original spin. When you look at the solar system's flatness, you're seeing an echo of its birth. You're seeing the shape of the primordial nebula frozen into the architecture of planetary orbits. The solar system is still, in a sense, the spinning cloud it used to be, just condensed, solidified, matured over billions of years. Venus rotates backward. Almost every other planet in the solar system spins in the same direction, counterclockwise when viewed from above the Sun's north pole. But Venus spins clockwise, slowly turning in the opposite direction, completing one rotation every 243 days. This retrograde rotation means the Sun rises in the west, on Venus, and sets in the east, backward from what we experience on Earth. But because Venus rotates so slowly, a sunrise on Venus isn't a quick event. Yeah, it takes weeks for the Sun to climb from the western horizon to its zenith, weeks more for it to descend toward the eastern horizon. The entire process of one day, from sunrise to sunset, unfolds over months of Earth time. We don't know for certain why Venus rotates backward. The leading theory is that something large hit Venus early in its history, a collision powerful enough to flip the planet's rotation. Or perhaps Venus's thick atmosphere creates tidal effects with the Sun that slowly reversed its spin over billions of years. Maybe it's some combination of both. The truth is, we're still not entirely sure. What we do know is that Venus took its own path, while the other planets spun in the direction inherited from the solar nebula. Venus went the other way, dancing to its own rhythm, turning backward through time, easy watching the Sun cross its sky in the wrong direction. It's a rebel world, toxic and strange, doing everything differently. Jupiter has at least 95 known moons, though that number keeps growing as we discover smaller and smaller satellites. Some are large and spherical, worlds in their own right. Others are tiny, irregular chunks of rock only a few miles across, probably captured asteroids that wandered too close to Jupiter's gravity well. Together, they form a miniature solar system, a family of worlds orbiting the giant planet like planets around a star. The four largest, Io, Europa, Ganymede and Callisto, discovered by Galileo in 1610, are fascinating worlds unto themselves. Io is covered in active volcanoes. Europa hides an ocean beneath its icy crust. Ganymede is larger than Mercury and generates its own magnetic field. Yet Callisto is ancient and heavily cratered, its surface a record of 4 billion years of impacts. Each is unique, each is complex, each could occupy scientists for generations. But Jupiter also has dozens of smaller moons we know almost nothing about. Some are only a mile or two across. Some have highly elliptical orbits that take them far from Jupiter before swinging back in close. Some orbit backward, suggesting they were captured rather than formed alongside Jupiter. They're irregular, chaotic, a collection of misfits and wanderers that Jupiter's gravity has gathered over billions of years. It's a reminder of how much complexity exists, even in our own cosmic neighborhood. Jupiter isn't just a planet. It's a system, a collection of worlds bound together by gravity, each with its own story, its own history, its own mysteries waiting to be unraveled. Earth has an invisible shield. You can't see it, can't feel it, but it's there. A bubble of magnetism extending hundreds of thousands of miles into space, wrapping around our planet like a protective cocoon. We call it the magnetosphere, and it's generated by the churning liquid iron in Earth's outer core. As this molten metal flows and convects, it creates electric currents, and those currents generate a magnetic field that extends far beyond the planet's surface. The magnetosphere reaches about 370,000 miles on the side facing away from the Sun, farther than the Moon. On the side facing the Sun, it's compressed by the solar wind to only about 40,000 miles. This asymmetry gives Earth's magnetic field a teardrop shape, with a long tail streaming away from the Sun like a comet. And it's a good thing this shield exists. The Sun constantly emits a stream of charged particles, protons and electrons moving at hundreds of miles per second. Without the magnetosphere, this solar wind would slam directly into Earth's atmosphere, slowly stripping it away. We know this happens because we've watched it happen to Mars. Mars lost its magnetic field billions of years ago, and the solar wind has been eroding its atmosphere ever since, thinning it to less than 1% of Earth's atmospheric pressure. The magnetosphere is why we still have air to breathe, oceans of liquid water, protection from radiation. It's an invisible guardian that's been deflecting the solar wind for billions of years, quietly preserving the conditions that make life possible, and most people never even know it's there. When we talk about gas giants, we usually mean Jupiter and Saturn, enormous planets made mostly of hydrogen and helium, so large that Earth could fit inside them hundreds of times over. But Uranus and Neptune are different. They're classified as ice giants, a distinct category because they contain much more water, methane, and ammonia than Jupiter or Saturn. These substances in planetary science are called ices, even though they're not actually frozen solid in the planet's interiors. Deep inside Uranus and Neptune, these ices exist under such extreme pressure and temperature that they behave strangely. They're not solid ice like you'd find in your freezer. They're not liquid water like in the ocean. They're something in between. Hot, dense fluids under pressures millions of times greater than Earth's atmospheric pressure. Under these conditions, water can be simultaneously above its boiling point and under such pressure that it can't evaporate. It becomes a supercritical fluid, a state of matter where the distinction between liquid and gas breaks down. So when we call Uranus and Neptune ice giants, we're not saying they're frozen. We're saying their interiors are dominated by these heavy compounds rather than just hydrogen and helium. They're structured differently from Jupiter and Saturn, with smaller rocky cores, thick mantles of exotic ices, and relatively thin atmospheres. It's a reminder that when we venture beyond Earth, even common substances like water behave in ways that seem impossible. The rules change, the familiar becomes strange, and planets can be made of materials in states we never encounter in our everyday lives. Saturn has a hexagon. At its north pole, then there's a cloud pattern that forms a nearly perfect six-sided shape. Each side of this hexagon is about 9,000 miles long, wider than Earth. The entire structure rotates with a period of 10 hours and 39 minutes, spinning with the planet's interior rotation rate. And it's been there, stable and persistent for at least 4 decades. When the Voyager spacecraft first spotted it in 1981, scientists weren't sure what to make of it. Hexagons don't occur naturally in weather patterns on Earth. We have circular storms, we have bands of winds, we have complex turbulent patterns, but nothing geometric like this. Yet there it was on Saturn, 6 straight sides meeting at nearly perfect angles, a shape that looked almost artificial. Later observations by the Cassini spacecraft confirmed it was real and still there. Scientists have developed theories involving jet streams and standing wave patterns. They've recreated hexagonal vortices in laboratory experiments by rotating fluids at specific speeds. But nobody fully understands why Saturn's hexagon is so stable, why it maintains those straight edges, why it's a hexagon rather than a pentagon or an octagon or some irregular polygon. The winds inside the hexagon blow at about 200 miles per hour, significantly different from the surrounding atmosphere. It's essentially a massive vortex with six-fold symmetry, and it's been spinning at Saturn's North Pole since before we discovered it, probably for centuries or millennia before that. A geometric storm on a world of chaos and clouds, precise and enduring for reasons we're still trying to fully understand. Mercury is unusual in how it's put together. Most rocky planets have an iron core that makes up maybe 30% of the planet's radius. Earth's core is about 55% of its radius, but Mercury's core accounts for about 75% of its radius. It's almost all core, with just a thin shell of rocky mantle and crust wrapped around it. This makes Mercury disproportionately dense and gives it a composition more like a planet's core than a whole planet. Scientists think they know why. Early in the solar system's history, when Mercury was still forming and the planets were still migrating and settling into their orbits, Mercury may have suffered a catastrophic collision with another large object. This impact could have blasted away much of Mercury's rocky mantle, stripping off the lighter materials and leaving behind the dense metallic core. So Mercury might be what's left after a planetary disaster, the surviving core of what was once a larger world. It's been stripped down to its iron heart, orbiting close to the Sun, baked and frozen in turn, a remnant of violence that happened billions of years ago. When you look at Mercury through a telescope, you're seeing a scar. You're seeing the exposed interior of a broken planet, still orbiting, still enduring, but forever marked by the collision that shaped it. It's the solar system's wounded world, carrying evidence of ancient trauma in its very structure. Mars has a day that's 24 hours and 37 minutes long, remarkably close to Earth's 24-hour day. This near match is purely coincidental. There's no physical reason why Mars's rotation should be so similar to ours. It just happened to form with a rotational period that almost exactly matches Earth's. But this coincidence has practical implications. If humans ever establish a permanent presence on Mars, our circadian rhythms, our internal biological clocks that regulate sleep and wakefulness, would adapt to Martian time much more easily than to any other planet. A Martian day, or sol as it's called, is close enough to an Earth day that our bodies wouldn't be thrown into complete disarray. Compare this to living on Venus, where a day lasts 243 Earth days, or Mercury, where the complex relationship between rotation and orbit creates a solar day 176 Earth days long. Human biology simply isn't equipped to handle that. Our sleep-wake cycles would become meaningless, but on Mars, you'd go to sleep and wake up on roughly the same schedule you're used to, as just shifted by 37 minutes each day. Over time, that 37-minute difference would accumulate. After about 40 days on Mars, your schedule would have drifted by about 24 hours relative to Earth time. But on a day-to-day basis, life on Mars would feel familiar in a way that life on any other planet wouldn't. You'd have mornings and evenings, nights and days, all unfolding at a pace your body understands. Jupiter's magnetic field is a monster. It's about 20,000 times stronger than Earth's, extending millions of miles into space. If you could see magnetic fields, Jupiter's magnetosphere would appear larger than the full moon when viewed from Earth, despite Jupiter being hundreds of millions of miles away. This enormous magnetic field is generated deep inside Jupiter, where the pressure is so intense that hydrogen is compressed into a metallic state. Metallic hydrogen conducts electricity, and as Jupiter rotates, it creates electric currents in this metallic layer. Those currents generate the magnetic field, which then extends outward, creating a vast magnetic bubble around the planet. Inside this magnetosphere, radiation levels are lethal. Charged particles from the solar wind get trapped by Jupiter's magnetic field and accelerate to enormous energies. The radiation near Jupiter is so intense that it would kill an unshielded human in minutes. Even spacecraft have to be specially hardened to survive in Jupiter's radiation environment. The Juno mission, currently orbiting Jupiter, has its sensitive electronics housed in a titanium vault just to protect them from the radiation. Jupiter's moon Io contributes to this radiation as well. Io's volcanoes spew out tons of sulfur and oxygen, which become ionized and trapped in Jupiter's magnetic field, creating a donut-shaped cloud of plasma around Jupiter's orbit. This Io plasma torus adds even more charged particles to the already dangerous environment. Jupiter's magnetosphere is a realm of invisible violence, a region of space where radiation and magnetism create one of the most hostile environments in the solar system. Neptune is blue, a deep, rich blue, more saturated and intense than Uranus's pale cyan. Both planets owe their colour to methane in their atmospheres, which absorbs red light and reflects blue light back into space. But Neptune's blue is darker, more vivid, suggesting there's something else in its atmosphere beyond just methane. Yes, scientists have long suspected that Neptune contains an unknown absorber, some substance or combination of substances that absorbs additional red light, intensifying the blue colour. But identifying what that substance is has proven difficult. It could be a particular form of methane ice or haze. It could be some complex hydrocarbon produced by chemical reactions in the atmosphere. It could be something we haven't even thought of yet. Recent research suggests it might involve a photochemical haze layer, essentially smog created when sunlight breaks down methane molecules, which then recombine into more complex compounds. These compounds could preferentially absorb red light, deepening Neptune's blue beyond what pure methane would produce. But we still don't have a definitive answer. Neptune's exact colour remains slightly mysterious, enhanced by some component we haven't fully identified. It's a small mystery perhaps, but it reminds us that even something as simple as why is that planet blue can still hold secrets. We can see Neptune clearly, we can measure its spectrum, we can analyse its light, and still there are questions we can't fully answer. Neptune hangs in the outer solar system, brilliantly blue, coloured by methane and mysteries. The word planet comes from ancient Greek. Planets means wanderer. To ancient astronomers, the planets were the wandering stars, lights in the sky that moved against the fixed backdrop of the constellations. While most stars maintained their positions relative to each other night after night, year after year, the planets drifted. They moved along the ecliptic, sometimes forward, sometimes appearing to move backward in retrograde motion, always travelling, always wandering. This wandering confused and fascinated ancient peoples. They developed elaborate models to explain it, epicycles upon epicycles, complex geometric arrangements designed to account for the planet's strange motions. They didn't know, of course, that these wandering stars were worlds like our own, or that Earth itself was one of them. They just knew these lights were different, special, worthy of attention and names. Eventually we figured it out. The planets don't actually wander randomly. They orbit the sun in elliptical paths, and their apparent motion across our sky is a result of both their orbit and ours. Retrograde motion happens when Earth overtakes an outer planet in its orbit, making the planet appear to move backward against the stars, an illusion of perspective, not actual backward motion. But the name stuck. We still call them planets, still honour that ancient observation that these objects are wanderers, and in a sense they still are. They're not fixed in place, they're moving, orbiting, wandering through space on journeys that will continue long after we're gone. Venus is a volcanic world. Its surface is covered with over 1,600 major volcanoes, more than any other planet in the solar system. Some are enormous shield volcanoes hundreds of miles across. Others are smaller, arranged in clusters and chains. Lava flows sprawl across vast plains, frozen in place, recording eruptions that happened millions of years ago. Most of Venus's volcanoes are probably extinct. The surface is geologically young, only 300 to 600 million years old, suggesting that massive volcanic resurfacing events happened in Venus's past, burying older terrains under fresh lava. But since then, volcanic activity has likely decreased. We don't see fresh lava flows that would indicate recent eruptions. However, some evidence suggests that Venus might still be volcanically active today. Spacecraft have detected changes in sulfur dioxide concentrations in Venus's atmosphere, which could indicate ongoing volcanic outgassing. Some radar observations have shown features that appear to change between different imaging sessions, possibly indicating fresh lava flows. And recent studies have identified regions where the surface appears hotter than surrounding areas, which could be sites of recent volcanic activity. But proving current volcanism on Venus is difficult. The planet's thick clouds hide the surface from direct observation. We can't watch eruptions in real time like we can on Earth or Io. We're left with indirect evidence, subtle clues, hints that Venus might still be a living world, still reshaping its surface, still pumping lava and gas from its interior onto its hellish landscape. Venus keeps its secrets well, hidden beneath clouds of sulfuric acid. Earth is the densest planet in the solar system. If you calculated the average density of every planet by dividing its mass by its volume, Earth would come out on top at about 5.5 grams per cubic centimetre. For comparison, water is 1.0 grams per cubic centimetre. Earth is 5.5 times denser than water. This high density comes from Earth's iron-nickel core and rocky mantle. We're made of heavy elements: iron, nickel, silicon, oxygen, magnesium. The gas giants are mostly hydrogen and helium, the lightest elements. Mercury is also very dense because of its large iron core, but Earth edges it out when you account for gravitational compression. Earth's own gravity compresses its interior, increasing its overall density. What this means is that Earth packs more matter into each cubic inch than any other world orbiting the Sun. We're the heaviest planet for our size, the most compact, the most tightly bound by our own gravity. And this density matters. It's part of why Earth has such a strong gravitational field relative to its size, why we can hold onto an atmosphere and oceans, why our interior remains hot and active enough to drive plate tectonics and generate a magnetic field. Earth is small compared to the gas giants, but we're dense, we're concentrated. We're a tight ball of rock and metal spinning through space, holding on to every atom with the fierce grip of our own gravity. And that density, that compactness, is part of what makes Earth the kind of world where liquid water can exist, where atmospheres can persist, where life can emerge. Saturn's rings are impossibly thin. They stretch 175,000 miles from edge to edge, wide enough to fit nearly 2 Earths side by side, but in most places they're only about 30 feet thick. Imagine taking something the width of a football field and making it thinner than a sheet of paper. That's the proportion we're talking about here. If you were to somehow stand in Saturn's rings, floating among the chunks of ice and rock, you'd see a strange sight. Looking along the plane of the rings, you'd see an endless expanse of orbiting material stretching to the horizon in all directions. But looking perpendicular to the rings, looking up or down, you'd see only a thin scattering of nearby particles, and beyond them, empty space. The rings would seem almost non-existent in that direction, a layer so thin you could pass through it in seconds. This thinness is maintained by collisions. When ring particles collide, they tend to dampen each other's vertical motion, gradually flattening the ring system over time. Any particle that strays too far above or below the ring plane will eventually collide with others and settle back into the flat disk. It's a self-organizing system, constantly flattening itself through billions of tiny collisions, and yet, from Earth, the rings appear as bright, solid bands of light. We see them edge on sometimes and they nearly disappear, a line so thin it's barely visible even through powerful telescopes. Then, as Saturn's axial tilt changes relative to Earth, we see them open up, revealing their full glory. But always, always, they remain impossibly thin, a cosmic disk of ice and rock, elegant and fragile and persistent. Mars once had a magnetic field. We know this because ancient rocks on Mars preserve a record of magnetization, frozen in place when the rocks formed and cooled in the presence of a global magnetic field. But about 4 billion years ago, something changed. Mars's magnetic field disappeared. The leading theory is that Mars's core cooled and solidified. A magnetic field requires a liquid, like conducting outer core, like Earth has, with convection currents that generate the field through a dynamo effect. When Mars's core solidified, or when the convection stopped, the magnetic field collapsed. And without that protective shield, the solar wind began its slow work of stripping away the Martian atmosphere. It happened gradually, over hundreds of millions of years. Charged particles from the Sun collided with the upper atmosphere, knocking atoms into space one by one. Without a magnetosphere to deflect the solar wind, nothing protected the atmosphere from erosion. Mars lost most of its air, its atmospheric pressure dropped to less than 1% of Earth's, and any liquid water on the surface would have evaporated or frozen. This is likely why Mars transformed from a potentially warm, wet world into the cold desert we see today. The loss of the magnetic field was the beginning of the end for habitable Mars. The planet didn't die in a catastrophe. It died slowly, bleeding its atmosphere into space over eons, unable to hold on to the conditions that might have supported life. Mars is a cautionary tale about the importance of planetary magnetic fields. Without that invisible shield, atmospheres can be lost, oceans can disappear, and entire worlds can become uninhabitable. Jupiter is a guardian. Its immense gravity, 2.5 times the mass of all other planets combined, acts as a cosmic vacuum cleaner, capturing or deflecting comets and asteroids that venture into the inner solar system. Many objects that might otherwise threaten Earth get pulled into Jupiter's gravitational well instead. We've watched this happen. In July 1994, Comet Shoemaker-Levy 9 collided with Jupiter in one of the most spectacular astronomical events ever witnessed. The comet had already been torn apart by Jupiter's gravity on a previous pass, fragmenting into more than 20 pieces. These fragments then crashed into Jupiter one after another over the course of a week, creating massive impact scars in Jupiter's atmosphere, some larger than Earth itself. If that comet had hit Earth instead, it would have been catastrophic on a global scale. But Jupiter absorbed it, its thick atmosphere and enormous size making the impacts almost negligible to the planet itself. Just another day in the life of the solar system's largest world. This protective role isn't absolute. Jupiter can also perturb objects and send them careening in unexpected directions, thus sometimes toward the inner solar system rather than away from it. But statistically, over billions of years, Jupiter's gravity has likely prevented countless impacts on Earth, clearing out much of the debris from the early solar system and reducing the bombardment rate of the inner planets. We orbit the Sun in a slightly safer neighbourhood because Jupiter exists. It's been standing guard for 4.5 billion years, absorbing hits meant for smaller worlds, quietly protecting the inner solar system without anyone noticing until recently. Uranus is colder than Neptune, even though Neptune is farther from the Sun. This doesn't make sense at first glance. Uranus orbits at about 1.8 billion miles from the Sun. Neptune orbits at about 2.8 billion miles. You'd expect the more distant planet to be colder. Yeah, but Uranus's upper atmosphere reaches temperatures of minus 371 degrees Fahrenheit, while Neptune's coldest regions only drop to about minus 353 degrees Fahrenheit. The difference comes down to internal heat. Neptune, like Jupiter and Saturn, emits more heat than it receives from the Sun. Its interior is still warm, still radiating energy left over from its formation. This internal heat warms Neptune's atmosphere from below, keeping temperatures slightly higher than they would otherwise be. Uranus mysteriously emits almost no excess heat. It radiates about as much energy as it absorbs from the Sun, with little to no internal heat contribution. Scientists believe the massive impact that knocked Uranus on its side billions of years ago may have also disrupted its internal heat flow, somehow allowing much of its primordial heat to escape. Or perhaps Uranus has an unusual internal structure that prevents heat from reaching the surface. Whatever the reason, Uranus is strangely cold for a giant planet. It's the coldest planetary atmosphere in the solar system, a frozen world spinning on its side, radiating away the faint warmth it receives from the distant Sun without any internal fire to supplement it. It's a broken planet in more ways than one, knocked over, heat-starved, spinning through the outer darkness colder than worlds that should by all rights be far more frigid. We call Jupiter and Saturn gas giants, but that's somewhat misleading. When you imagine a gas, you probably think of air, invisible, thin, easy to pass through. But Jupiter and Saturn don't have surfaces you could stand on, not in the traditional sense. And their interiors are nothing like the air you breathe. As you descend into Jupiter's atmosphere, the pressure increases gradually. The gas gets thicker, denser, more resistant. Eventually, the pressure becomes so extreme that the hydrogen gas transitions into a liquid. Not through cooling, the interior of Jupiter is hot, but purely through compression. The atoms are squeezed so tightly together that the gas condenses into a liquid state. Go deeper still, and something even stranger happens. At pressures millions of times greater than Earth's atmosphere, hydrogen enters a state called metallic hydrogen. The immense pressure strips electrons away from hydrogen atoms, allowing them to move freely like electrons in a metal. This metallic hydrogen conducts electricity, and it's this layer that generates Jupiter's powerful magnetic field as the planet rotates. So Jupiter isn't really made of gas in the way we usually think of gas. It's a world of gradients and transitions, where gas becomes liquid, becomes something exotic and strange, where there's no clear boundary between layers, just smooth transitions from one state of matter to another. You couldn't land on Jupiter because there's nowhere to land. You just sink deeper and deeper into increasingly dense material until the pressure crushed you, without ever hitting a solid surface. Mercury's surface is ancient and scarred. It's covered in billions of impact craters, layer upon layer of them, overlapping and crowding together in a landscape that preserves the history of 4 billion years of cosmic bombardment. Some of these craters are small, just meters across. Others are enormous basins hundreds of miles wide, created by asteroids the size of mountains. The youngest craters, and by young we mean millions of years old, still have bright rays extending from them. These rays are made of material ejected during the impact, thrown outward in straight lines radiating from the crater. On the Moon, these rays eventually darken. A solar wind and micrometeorite impacts weather them. On Mercury, the same process happens, but we can still see rays around relatively fresh craters, marking them as the most recent wounds in Mercury's ancient surface. There's almost no erosion on Mercury, no wind, no water, no plate tectonics to reshape the surface. Once a crater forms, it stays essentially unchanged for billions of years. The only thing that can erase it is another impact, or a newer crater that overlaps and destroys the old one. Mercury's surface is like a palimpsest, a manuscript written over and over again, each new impact adding to the story, covering older features with new scars. When you look at Mercury, you're seeing a record. You're seeing the history of the solar system written in impact craters, a timeline of collisions stretching back to the planet's formation. Every crater is a moment frozen in stone, a day when an asteroid fell, when debris rained across the surface, when another scar was added to this battered world. Earth's atmosphere doesn't have a sharp boundary. It doesn't end at some specific altitude where air suddenly gives way to the vacuum of space. Instead, it gradually thins as you ascend, becoming less and less dense, and until eventually there are so few molecules that it's effectively a vacuum, but technically you're still in Earth's atmosphere. The Kármán line at 62 miles altitude is often cited as the boundary of space, but that's just an arbitrary definition. Air molecules exist well beyond that point. In fact, Earth's atmosphere extends much farther than most people realize. The exosphere, the outermost layer of the atmosphere, reaches about 6,200 miles above the surface, halfway to the Moon. At that altitude, the atmosphere is incredibly thin. You might find only a handful of atoms per cubic meter, compared to trillions upon trillions at sea level. But those atoms are still gravitationally bound to Earth, still technically part of our atmosphere. They orbit the planet in highly elliptical paths, occasionally colliding with other atoms, and slowly exchanging energy until they either fall back toward Earth or gain enough speed to escape into space entirely. So in a sense, Earth's atmosphere brushes against the Moon. The boundary between Earth and space isn't a line, it's a gradual fade. a slow transition from breathable air to the near vacuum of interplanetary space, and that transition extends much farther than the few dozen miles where the sky turns black and stars become visible in daytime. Earth's influence reaches far beyond the blue horizon. Neptune takes 165 Earth years to complete one orbit around the Sun. That's an almost incomprehensibly long time by human standards. Neptune was discovered on September 23, 1846, through mathematical predictions rather than direct observation, and it didn't complete its first full orbit since discovery until July 12, 2011. Well, think about what that means. In all of human history, all of recorded civilization, from ancient Sumer to the present day, Neptune has completed only a tiny fraction of its orbits. The planet has circled the Sun perhaps 27 or 28 times since humans invented writing. Since the pyramids were built, Neptune has orbited about 20 times. Since Neptune's discovery, we've observed it for just slightly more than one complete Neptunian year. Everything we know about Neptune we've learned in less time than it takes the planet to make one circuit around the Sun. We don't know what a full seasonal cycle on Neptune looks like, because we haven't observed one yet. We don't know if there are long-term changes in Neptune's atmosphere that only become apparent over multiple decades or centuries, as Neptune moves through space at about 12,000 miles per hour in its orbit. But from our perspective, it barely seems to move at all. It drifts slowly against the background stars, taking years to cross a single constellation. It's patient in a way we can't truly comprehend, measuring time in centuries while we count hours and days. Venus is the brightest natural object in Earth's night sky after the Moon. On clear nights, when Venus is at its brightest, it can cast faint shadows on the ground. People throughout history have noticed Venus without understanding what it was. A brilliant point of light appearing in the west after sunset or in the east before sunrise. Ancient civilizations often thought Venus was two different objects. The Greeks called it Phosphorus when it appeared as the morning star and Hesperus when it appeared as the evening star. They eventually realized these were the same object, but the dual identity of Venus persisted in mythology and culture for centuries. The reason Venus shines so brightly is its thick cloud cover. Those clouds reflect about 70% of the sunlight that hits them. Venus is also relatively close to Earth at its nearest approach, only about 25 million miles away, closer than any other planet. This combination of high reflectivity and proximity makes Venus visible even in twilight, sometimes even during the day if you know exactly where to look. But that brightness hides a hellish world. Those beautiful reflective clouds are made of sulfuric acid. The surface below is hot enough to melt lead, and Venus presents itself to us as a beacon of light, the evening star, a symbol of beauty in cultures around the world. And beneath that brilliant exterior is one of the most hostile environments in the solar system. Venus is beautiful from a distance, like so many dangerous things are. The four gas giants, Jupiter, Saturn, Uranus, and Neptune, contain 99% of all the mass in the solar system that isn't in the Sun. Let that sink in for a moment. Everything else, Mercury, Venus, Earth, Mars, all the moons, all the asteroids, all the comets, all the dust and debris scattered throughout the solar system, accounts for only about 1% of the non-solar mass. The Sun itself contains about 99.86% of the entire solar system's mass. The gas giants contain most of what's left. The rocky planets, despite being where we live, despite being the worlds we can actually walk on, are almost negligible in terms of mass. Jupiter alone is more than twice as massive as all the other planets combined. This lopsided distribution tells us something about how the solar system formed. The outer regions of the solar nebula were cold enough for ices to condense, and there was more material available. Jupiter and Saturn grew massive enough to gravitationally capture hydrogen and helium directly from the nebula. The inner solar system was warmer, with only rocky materials condensing, and those rocks formed smaller worlds. We live on a minor world in a solar system dominated by giants. Earth is important to us, obviously. It's our home, the only place in the universe we know harbours life. But in terms of mass, in terms of gravitational influence, in terms of sheer physical presence, we're a footnote. The solar system belongs to the Sun and the gas giants. The rest of us are just filling in the spaces between. Mars has polar ice caps just like Earth. You can see them through telescopes, brilliant white patches at the north and south poles, growing and shrinking with the Martian seasons. But unlike Earth's ice caps, which are made almost entirely of water ice, Mars's polar caps are a mixture of water ice and frozen carbon dioxide, dry ice. During the Martian winter, temperatures at the poles drop low enough for carbon dioxide to freeze out of the atmosphere. The air itself condenses and falls as snow, adding layers of dry ice to the polar caps. In some winters, up to 30% of Mars's entire atmosphere freezes and deposits at the poles. The atmospheric pressure drops measurably across the entire planet as all that gas turns solid. Then, when spring arrives, the dry ice sublimes. It turns directly from solid to gas without melting, and returns to the atmosphere. The polar cap shrinks. The atmospheric pressure rises again, and the cycle continues. It's a planetary breathing pattern, Mars exhaling and inhaling its atmosphere with each seasonal cycle. Beneath the seasonal layer of carbon dioxide ice lies a permanent cap of water ice, particularly at the North Pole. This ice is ancient, possibly billions of years old, containing a record of Mars's climate history in its layers. If you could drill down through that ice, you'd be reading a book about Mars's past written in frozen water and dust. Mars's polar caps are beautiful from orbit, swirling patterns of ice and dark dust, or changing with the seasons, growing and receding in a rhythm that's been playing out for billions of years under that salmon-coloured sky. Saturn's moon Titan has lakes and seas on its surface. Not water. It's far too cold for liquid water on Titan. Instead, these are seas of liquid methane and ethane, hydrocarbons that exist as gases on Earth but condense into liquids in Titan's frigid temperatures of -290 degrees Fahrenheit. Titan is the only world besides Earth where we've found stable liquids on the surface. The Cassini spacecraft mapped these lakes with radar, revealing smooth liquid surfaces surrounded by shorelines, river channels feeding into them, and what appear to be seasonal variations in their levels. The largest, Kraken Mare, is bigger than the Caspian Sea. It's a genuine ocean, just made of methane instead of water. And Titan has a methane cycle analogous to Earth's water cycle. Methane evaporates from the lakes and seas, rises into Titan's thick atmosphere, condenses into clouds, and falls as rain. That rain carves river channels, erodes the landscape, and flows back into the lakes. It's weather and geology driven by methane instead of water, an alien reflection of processes we find familiar. Standing on the shore of a Titan lake would be surreal. The liquid would be clear but might have a slight amber tint. The atmosphere is so thick that sound would travel differently, deeper, more muffled. the sky would be orange from the haze of complex organic molecules in the atmosphere, and waves, driven by Titan's gentle winds, would lap against the shore, made of methane, following the same physical laws that govern Earth's oceans. But in a world utterly unlike our own, Jupiter rotates faster than any other planet in the solar system. Despite being enormous, 11 times wider than Earth, Jupiter completes one full rotation in just under 10 hours. If you were standing on a cloud top at Jupiter's equator, hypothetically since there's no surface to stand on, you'd be moving at about 28,000 miles per hour as the planet spins. This rapid rotation has visible effects. Jupiter is noticeably flattened at the poles. The equatorial diameter is about 6% larger than the polar diameter. You can see this ablateness in photographs. Jupiter looks squashed, bulging at the middle like a ball that's been compressed from top and bottom. The rapid spin also drives Jupiter's weather patterns. Those distinctive bands of clouds, the light zones and dark belts that stripe the planet, are arranged parallel to the equator, organized by Jupiter's rotation. The Great Red Spot and other storms are caught up in this rotation, swept around the planet by winds that can exceed 400 miles per hour. And because different parts of Jupiter rotate at different speeds, it's a fluid planet without a solid surface. The rotation period varies with latitude. The equator rotates faster than the poles. This differential rotation creates shear between different atmospheric layers, contributing to the complex, turbulent weather patterns we observe. Jupiter is a spinning dervish, a world rotating so fast it's reshaping itself, creating storms and winds and cloud patterns through the sheer force of its rotation. Yeah, it's been spinning this way for billions of years, and it will continue for billions more. The planet's formed from a disk of gas and dust surrounding the young sun about 4.6 billion years ago. This disk, called the Solar Nebula, was made of hydrogen, helium, and heavier elements, the debris left over after the sun's formation. It started with tiny grains of dust, smaller than the width of a human hair. These grains drifted through the nebula, occasionally colliding and sticking together through static electricity and chemical bonds. Grain by grain, they grew into larger particles. Those particles collided and merged into pebbles. Pebbles accumulated into boulders, boulders into larger rocks. Eventually, some of these accumulations grew large enough that their own gravity began to matter. They started pulling in nearby material, growing faster and faster. These became planetesimals, objects miles or tens of miles across, and the planetesimals continued colliding, merging, growing into larger and larger bodies. In the inner solar system, where it was hot, only rocky materials and metals could condense. These formed the rocky planets, Mercury, Venus, Earth, Mars. In the outer solar system, beyond the frost line where temperatures were cold enough for ices to condense, there was much more material available. Rocky and icy planetesimals grew into massive cores, and some grew large enough to gravitationally capture gas directly from the nebula, becoming Jupiter and Saturn. The entire process took perhaps 10 to 100 million years. We're living on condensed stardust, assembled grain by grain from the debris cloud surrounding an infant star, a slowly accumulating mass until gravity shaped us into worlds. Mercury has almost no atmosphere, just an exosphere, an incredibly thin layer of atoms that barely qualifies as an atmosphere at all. The pressure at Mercury's surface is about 1/4 of Earth's atmospheric pressure. For practical purposes, it's a vacuum. This exosphere is made of atoms that have been knocked off Mercury's surface by solar wind particles and micrometeorites. Sodium, potassium, calcium, magnesium. These atoms are blasted free from the rocks, drift briefly above the surface, and then either fall back down or escape into space. The exosphere is constantly being eroded away and constantly being replenished, but it never accumulates into anything substantial. Without an atmosphere, Mercury's sky is always black, even at noon, and stars would be visible alongside the sun. There's no blue scattering like on Earth, no diffusion of sunlight, just the stark contrast between the brilliant sun and the black of space. And without atmospheric pressure, there's no sound. Sound needs a medium to travel through, air molecules vibrating and passing that vibration along. On Mercury, there's essentially nothing to carry sound. If you stood on Mercury's surface and clapped your hands, you'd feel the impact but hear nothing. An explosion would produce a flash of light and a shower of debris but no sound whatsoever. It would be a world of perfect silence. Mercury is exposed, vulnerable, bombarded by radiation and solar wind without any protective blanket. It's a naked world, its surface directly facing the vacuum of space, scorched by the nearby sun in airless silence. Earth's axis is tilted at 23.5 degrees relative to the plane of its orbit around the sun. This tilt is why we have seasons. As Earth orbits the sun, different parts of the planet tilt toward or away from the sun at different times of year. When the northern hemisphere tilts toward the sun, that hemisphere receives more direct sunlight, and days are longer than nights. This is summer in the north. At the same time, the southern hemisphere tilts away, receiving less direct sunlight, with shorter days, winter in the south. 6 months later, the situation reverses. Without this tilt, there would be no seasons. Every location on Earth would experience roughly the same temperatures year-round. The equator would be perpetually hot, the poles perpetually cold, and temperate zones would remain temperate. Our day length would be constant throughout the year, always 12 hours of daylight and 12 hours of darkness. But because Earth is tilted, we get the slow rhythm of seasons, spring's awakening as days lengthen and warmth returns, summer's long bright evenings and growing heat, autumn's gradual cooling and shortening days, winter's cold darkness and dormancy. This cycle drives so much of life on Earth. Migration patterns, hibernation, plant growth cycles, harvest seasons. A 23.5 degree tilt might seem arbitrary, but it's shaped the entire character of life on Earth. It's given us variety, change, rhythm. It's made Earth a planet of seasons, where time is marked not just by orbits, but by the changing angle of sunlight. Neptune has storms that come and go, unlike Jupiter's persistent Great Red Spot. When Voyager 2 flew past Neptune in 1989, it spotted a massive storm system called the Great Dark Spot, an oval storm about the size of Earth, with winds exceeding 1,500 miles per hour. It looked similar to Jupiter's Great Red Spot, and scientists wondered if it might be equally long-lived. But when the Hubble Space Telescope looked at Neptune in 1994, the Great Dark Spot had vanished, completely gone. In its place, new storms had formed in different locations. Neptune's atmosphere, it turns out, is more dynamic than Jupiter's. Storms form, rage for a few years or decades, and then dissipate, replaced by new storms elsewhere. We've continued to observe Neptune, and this pattern holds. Dark spots appear, drift, change shape, and eventually fade away. Neptune's atmosphere is constantly churning, constantly reorganizing itself, never settling into the stable long-term patterns we see on Jupiter. Why the difference? We're not entirely sure. It might be related to Neptune's internal heat source. The planet radiates more energy than it receives from the Sun, and this internal heat might drive more vigorous atmospheric circulation. Or it might be related to Neptune's smaller size or different atmospheric composition. Whatever the reason, Neptune refuses to maintain persistent storms. It's a more temperamental planet than Jupiter, its weather constantly shifting, its great storms appearing and disappearing like thoughts, leaving no permanent mark on the atmosphere's pale blue expanse. Venus's clouds are made of sulfuric acid, not water vapor, not ammonia or methane like on the gas giants, but concentrated sulfuric acid, the same corrosive chemical used in car batteries and industrial processes. These acid clouds form about 30 to 40 miles above Venus's surface, in a layer where temperatures are cool enough for sulfuric acid to condense from sulfur dioxide and water vapor. The clouds are thick enough to completely hide the surface from view. From space you can't see through them. All we see is a smooth, featureless white globe, beautiful and utterly opaque. Sometimes it rains on Venus. Droplets of sulfuric acid form in the clouds and begin to fall. But Venus's surface is so hot, around 900 degrees Fahrenheit, that the acid droplets evaporate long before they reach the ground. This creates what's called virga, streaks of rain falling from clouds but disappearing into the atmosphere before hitting the surface. On Venus, it rains acid that never lands. The clouds themselves are part of what makes Venus so hot. They're highly reflective, which is why Venus shines so brightly in our sky, but they also trap infrared radiation. Heat from the surface tries to radiate into space, but the thick clouds and carbon dioxide atmosphere trap it, creating a runaway greenhouse effect. The clouds keep Venus's surface at an even 900 degrees Fahrenheit day and night everywhere on the planet. Venus hides behind its toxic veil, bright and beautiful from a distance, deadly up close, a world of acid clouds and heat that would melt lead. Between Mars and Jupiter lies the asteroid belt, a region of space filled with millions of rocky objects ranging from dust grains to dwarf planets. The largest series is about 590 miles in diameter. Most are much smaller, just rubble tumbling through space. Like these asteroids are the remnants of a planet that never formed. In the early solar system, rocky material in this region began to accumulate, just like it did elsewhere. Planetesimals formed and started growing. But Jupiter's gravity disrupted the process. The giant planet's gravitational influence stirred up the asteroid belt, increasing collision velocities. Instead of gently merging when they collided, asteroids began to shatter, breaking apart rather than accumulating. So the asteroid belt remains a field of debris, prevented from coalescing into a planet by Jupiter's gravitational interference. If you added up all the mass in the asteroid belt, it would only be about 4% of the Moon's mass, not enough to form a significant planet even if it could merge. Despite its name and its depiction in science fiction, the asteroid belt is mostly empty space. The asteroids are spread out over such a vast volume that spacecraft can pass through the belt with virtually no risk of collision. If you were somehow standing on an asteroid, you'd probably see a few other asteroids as distant points of light, but mostly you'd just see empty space and stars. The asteroid belt is a graveyard of a planet that could have been scattered rubble held in eternal orbit, prevented from ever becoming whole. Saturn is the most oblate planet in our solar system. Oblateness is a measure of how much a planet is flattened at the poles compared to its equator. On a perfectly spherical planet, the polar and equatorial diameters would be identical. But most planets bulge slightly at the equator due to their rotation. Saturn bulges a lot. Its equatorial diameter is about 74,900 miles, but its polar diameter is only about 67,600 miles, almost 10% smaller. You can see this flattening in photographs. Saturn doesn't look quite round, it looks squashed, compressed from top and bottom. This extreme oblateness comes from Saturn's combination of rapid rotation and low density. Saturn spins once every 10.7 hours, and it's made mostly of hydrogen and helium, the lightest elements. The rapid rotation creates centrifugal force that pushes material outward at the equator, and the low-density material doesn't resist this deformation strongly. So Saturn spreads out at the equator, creating that visible squashed appearance. If Saturn were denser or rotated more slowly, it would be rounder. If it were less dense or rotated faster, it would be even flatter. Saturn sits at a particular balance point, fast rotation, low density, creating the most oblate planet we know of, visibly distorted by its own spin. It's a reminder that planets aren't perfect spheres. They're dynamic objects, shaped by rotation and gravity and internal structure, and sometimes those forces create visible deformations that make them look almost impossible, almost artificial in their strangeness. Mars has an atmosphere, but it's incredibly thin, only about 1% as thick as Earth's. If you stood on Mars without a spacesuit, the low pressure would be lethal within seconds. Your blood would begin to boil at body temperature, not from heat but from the lack of atmospheric pressure keeping it liquid. That thin atmosphere is 95% carbon dioxide, with traces of nitrogen and argon. There's almost no oxygen, no breathable air, and because it's so thin, it provides almost no insulation. Heat radiates away from the surface quickly once the sun sets. During a Martian day, temperatures near the equator might reach a relatively comfortable 70 degrees Fahrenheit. But at night, in that same location, temperatures can plummet to minus 100 degrees Fahrenheit or lower. This day-night temperature swing of over 100 degrees is extreme by Earth standards. Our atmosphere redistributes heat, moderating temperature changes between day and night. Mars's thin atmosphere can't do that effectively. Each location heats up quickly when the sun rises and cools rapidly when it sets, creating wild temperature variations within a single day. The thin atmosphere also means there's little protection from radiation. Cosmic rays and solar radiation strike the surface with much more intensity than on Earth. Any life on Mars, either past or present, would have needed to cope with this radiation somehow, perhaps living underground, perhaps protected by water or soil. Mars's atmosphere is a whisper, a ghost of what it might once have been, barely there at all, unable to shield or warm or sustain the surface beneath it. Europa, one of Jupiter's 4 large moons, is covered in a smooth shell of water ice. But beneath that ice lies an ocean, a global ocean of liquid water that may be twice as deep as the Mariana Trench, the deepest point in Earth's oceans. Europa's ocean exists because of tidal heating. As Europa orbits Jupiter, the giant planet's gravity squeezes and stretches the moon. Europa's orbit is slightly elliptical, so the tidal forces vary as it moves closer to and farther from Jupiter. This constant flexing generates heat through friction. enough to keep the subsurface water liquid despite the frigid temperatures of the outer solar system. The ice shell above the ocean is perhaps 10 to 15 miles thick in most places, though it might be thinner in some areas. We've seen evidence of this ocean reaching the surface. Geysers of water vapor erupting from cracks in the ice, photographed by the Hubble Space Telescope. These plumes suggest the ocean is in contact with the surface, at least occasionally, bringing deep water up to the icy crust. Why does this matter? Because on Earth, wherever we find liquid water, we find life. Europa's ocean might have all the ingredients necessary for life. Liquid water, chemical energy from the tidal heating, and organic compounds delivered by comets and asteroids over billions of years. There might be hydrothermal vents on Europa's ocean floor, at least similar to those on Earth where entire ecosystems thrive in complete darkness. Europa might be a living world, its ocean hidden beneath kilometers of ice, sheltered from Jupiter's radiation, potentially harboring life we've never imagined. Uranus has 27 known moons, and unlike most moons in the solar system, they're not named after mythological figures. Instead, they're named after characters from the works of William Shakespeare and Alexander Pope. There's Titania and Oberon, the king and queen of the fairies from A Midsummer Night's Dream. Miranda from The Tempest. Ariel and Umbriel from Pope's The Rape of the Lock. Puck, Cordelia, Ophelia, Desdemona, characters from Shakespeare's plays, orbiting a tilted world in the outer solar system. This naming convention was established by John Herschel, the son of William Herschel, who discovered Uranus. The tradition has continued as new moons have been discovered, drawing from an increasingly obscure collection of literary characters. Some of Uranus's smallest moons are named after minor characters most people have never heard of: Cupid, Mab, Perdita, Francisco. It's a peculiar thing, this literary connection. While Jupiter's moons bear the names of Zeus's lovers and children, and Saturn's moons are named for titans and giants, Uranus's satellites carry the names of sprites and tragic heroines, kings and fools, characters from poetry and theatre. They're artistic rather than mythological, human creations rather than ancient gods. Perhaps it's fitting for a planet as strange as Uranus, sideways, cold, emitting almost no heat, that its moons should also be different, a name not for deities but for the creations of human imagination, for characters that never existed except in words and stories. Earth's moon is unusually large relative to its planet. The moon is about 27% the diameter of Earth, proportionally the largest moon in the solar system, excluding Pluto and Charon, which some scientists consider a double dwarf planet system rather than a planet-moon pair. Most planets' moons are tiny compared to the planet they orbit. Jupiter's largest moon, Ganymede, is less than 4% of Jupiter's diameter. Saturn's largest moon, Titan, is less than 5% of Saturn's diameter. But Earth's moon is over a quarter of Earth's size, large enough to create significant tidal effects, to stabilize Earth's axial tilt, to be visible in the sky as a disk rather than just a point of light. This large size is why some astronomers refer to the Earth-Moon system as a double planet rather than a planet and satellite. The Moon doesn't orbit around Earth's center. Both bodies orbit around their common center of mass, called the barycenter. That barycenter is inside Earth, but only about 1,000 miles below the surface, much closer to the surface than to the center. The Moon's size and proximity have shaped life on Earth. The tides it creates, rising and falling ocean levels driven by the Moon's gravity, have influenced coastal ecosystems for billions of years. The moon stabilizes Earth's axial tilt, preventing wild swings in climate, and the moon's presence may have been crucial in the early formation of life, creating tidal pools and coastal environments where chemistry could become biology. We live in a double planet system, are orbiting the sun together, bound by gravity in a dance that's lasted for over 4 billion years. Neptune's winds blow in the opposite direction to its rotation. On Earth, our strongest winds generally blow in the same direction the planet rotates. But on Neptune, the fastest winds, those howling at over 1,200 miles per hour, blow westward, retrograde, against the direction of the planet's rotation. This is deeply strange and not fully understood. Wind is driven by differential heating and the planet's rotation, which normally causes winds to flow in the same direction as the spin. But Neptune's winds violate this expectation. They're moving backward relative to the planet's rotation, driven by some mechanism that overrides the normal pattern. It might be related to Neptune's internal heat. The planet radiates more than twice as much energy as it receives from the sun. This internal heat might drive convection currents that rise from deep within the atmosphere and create wind patterns that don't follow the typical rules. Or there might be some interaction between different atmospheric layers, with the visible cloud tops moving independently of the deeper atmosphere. Whatever the cause, Neptune's winds are doing something that shouldn't be possible according to our basic understanding of planetary atmospheres. They're supersonic, retrograde, and more powerful than any wind system we've observed on any other planet. Neptune is defying expectations, spinning one way while its atmosphere rushes the other way, creating a dynamic tension that manifests as the fastest winds in the solar system. It's another reminder that Neptune, as distant and dark, holds mysteries we're only beginning to unravel. Mercury experiences the greatest temperature variation of any planet in the solar system. During the day, when the sun hangs high in Mercury's black sky, surface temperatures can reach 800 degrees Fahrenheit, hot enough to melt lead and zinc. But at night, with no atmosphere to retain heat, temperatures plummet to minus 290 degrees Fahrenheit. That's a temperature range of over 1,000 degrees Fahrenheit between day and night. On Earth, our atmosphere redistributes heat, carrying warmth from the day side to the night side, moderating temperature swings. Even in deserts, where day-night temperature variations are most extreme, we might see swings of 50 or 60 degrees, maybe 80 in the most extreme locations. But Mercury, with essentially no atmosphere, experiences temperature changes more than 10 times larger. If you could somehow stand on Mercury's surface, protected from the heat and radiation, you'd watch the sun rise and the temperature soar from hundreds of degrees below zero to hundreds of degrees above, all in the span of a few Earth days. Then, as the sun set and the long Mercurian night began, lasting 88 Earth days, you'd feel the heat radiating away into space, the ground cooling rapidly until it reached temperatures colder than anywhere on Earth. Mercury is a world of extremes, swinging between furnace and freezer, baked on one side and frozen on the other, with no atmosphere to soften the transition. It's the solar system's most temperature-volatile world, experiencing climate swings that would shatter most materials, caught between the unfiltered fury of the nearby sun and the absolute cold of shadowed space. Jupiter emits radio waves powerful enough to be detected by amateur radio equipment on Earth. These aren't radio signals in the sense of communication. They're natural emissions generated by charged particles spiraling along Jupiter's magnetic field lines. The process is called synchrotron radiation. Electrons from Jupiter's magnetosphere, some captured from the solar wind, some ejected from volcanoes on the moon Io, accelerate along the planet's magnetic field lines at nearly the speed of light. As they spiral in this magnetic field, they emit radio waves at specific frequencies, primarily in the decameter wavelength range. These radio bursts can be quite strong. Sometimes they're intense enough that amateur radio enthusiasts can detect them using simple equipment, just a radio receiver and a basic antenna. Jupiter announces its presence across the solar system, broadcasting on radio frequencies, creating static and noise that propagates through space at the speed of light. It's one of the few astronomical phenomena accessible to amateur equipment without a telescope. You don't need to see Jupiter to detect it. You can hear it, in a sense, as radio noise created by invisible processes happening millions of miles away. Jupiter's magnetic field, its trapped radiation, its interaction with its moons. All of this creates a radio signature, a cosmic static that's been broadcasting since before humans existed to listen. Jupiter has been sending these radio signals for billions of years, filling the solar system with electromagnetic noise, a natural radio station operating on frequencies we only learned to detect in the 20th century. Venus rotates so slowly that its atmosphere circles the planet much faster than the surface spins. This phenomenon is called superrotation, and it's one of the strangest aspects of Venusian meteorology. Venus's solid body takes 243 Earth days to complete one rotation. But high in Venus's atmosphere, winds race around the planet in only about 4 Earth days. That means the upper atmosphere is moving about 60 times faster than the surface. Winds of over 200 miles per hour at cloud top level, circling the entire planet while the surface beneath barely moves. We don't fully understand why this happens. Superrotation violates what we'd normally expect from atmospheric dynamics. On Earth, the fastest winds are much slower than the planet's rotation. But on Venus, the atmosphere has somehow decoupled from the surface, developing its own rapid circulation pattern that ignores the sluggish rotation of the planet below. Several mechanisms might contribute. Solar heating at the cloud tops could drive large-scale convection. Atmospheric tides raised by the sun might transfer momentum to the upper atmosphere. Thermal gradients between the day and night sides could create pressure differences that drive winds. But no single theory fully explains the observations. Venus's atmosphere is doing its own thing, spinning independently of the planet, racing around the world while the surface turns at a crawl. It's a decoupled system, 2 different rotation rates existing on the same world, creating weather patterns unlike anything we see on Earth. The 4 inner planets, Mercury, Venus, Earth and Mars, are called terrestrial planets. The term comes from the Latin word terra, meaning earth. These are the Earth-like worlds, the rocky planets, the ones with solid surfaces you could theoretically walk on. They share similar basic structures: a metal core, usually iron and nickel, surrounded by a rocky mantle and a thin crust. They're all relatively small. Mars is the largest of the terrestrial planets besides Earth, and it's only about half Earth's diameter. They're all closer to the Sun than the asteroid belt, occupying the inner region of the solar system where temperatures were too high for ices to condense during planetary formation. But within these similarities there's tremendous variety. Mercury is airless and cratered, its surface baked and frozen in turn. Venus has a thick toxic atmosphere and surface temperatures hot enough to melt lead. Our Earth has oceans and life and a protective magnetic field. Mars is a frozen desert with a thin atmosphere and ancient river valleys. They're terrestrial planets, yes, made of rock and metal, solid and dense, but each followed its own evolutionary path shaped by different factors: size, distance from the Sun, the presence or absence of a magnetic field, the retention or loss of atmosphere and water. They started from similar ingredients but became radically different worlds. The terrestrial planets are Earth's family, sharing a common origin and structure, but each one unique, each one a different answer to the question of what a rocky planet can become. Saturn's rings are young, much younger than Saturn itself. While the planet formed about 4.5 billion years ago along with the rest of the solar system, the rings are probably only 100 to 200 million years old at most. Some estimates suggest they might be even younger, perhaps only 10 to 100 million years old. We can tell the rings are young from how clean and bright they are. They're made mostly of water ice, and over time that ice should darken as it's contaminated by dust and micrometeorite impacts. But Saturn's rings are very bright, very reflective, suggesting they haven't had time to accumulate much darkening material. So where did the rings come from if they're so much younger than Saturn? The leading theory is that they're the remains of a moon that wandered too close to Saturn and was torn apart by tidal forces, or that was shattered by a collision with a comet or asteroid. The debris from this destruction spread out into Saturn's equatorial plane and are forming the rings we see today. This means Saturn hasn't always had rings. For most of its existence, for billions of years, Saturn was ringless. The rings are a recent development, cosmically speaking, a temporary adornment that won't last forever. They're being slowly eroded, slowly spiraling inward and raining down onto Saturn. In another 100 million years, they might be gone entirely. We're living in a special time, a brief window in the solar system's history, when Saturn has spectacular rings. It's a temporary beauty, a fleeting configuration that won't last, making it all the more precious. Mars has a canyon system called Valles Marineris that stretches over 2,500 miles across its surface, long enough to span the entire continental United States from New York to Los Angeles. It's about 125 miles wide at its broadest point and plunges down nearly 23,000 feet in some places, more than 4 times deeper than the Grand Canyon. If you stood at one end of Valles Marineris and looked toward the other end, you wouldn't see the far side. It would curve beyond the horizon, disappearing into the distance like an ocean. The walls of the canyon would tower above you, cliffs of layered rock rising miles into the thin Martian sky, carved and shaped by processes we're still trying to fully understand. Valles Marineris probably formed through a combination of tectonic fracturing and erosion. As the Tharsis region, home to Mars's largest volcanoes, bulged upward billions of years ago, it created enormous stresses in the crust. The ground cracked, forming a series of parallel faults. Over time, these cracks widened, as water may have flowed through them, carving them deeper. Landslides and wind erosion continued to shape the canyon walls. Unlike Earth's Grand Canyon, which was carved by a river over millions of years, Valles Marineris formed through tectonic forces, the Martian crust literally pulling apart. It's a crack in the planet, a wound that never healed, a testament to forces powerful enough to fracture an entire world. Standing on the rim of Valles Marineris would give you a sense of scale that's hard to comprehend. A valley so vast it defies human perception, stretching beyond sight, deeper than any canyon on Earth. Earth's oceans contain about 321 million cubic miles of water. That sounds like an enormous amount, and it is by human standards enough water to cover the entire United States to a depth of about 90 miles. But in terms of Earth's total mass, water represents less than 0.05%. Most of Earth is rock and metal. The water we see covering about 71% of the surface is just a thin film, a coating spread across the planet's exterior. If you shrank Earth down to the size of a basketball, all the water in all the oceans would fit into a volume smaller than a ping-pong ball. It's a vanishingly small fraction of the planet's total bulk, and yet that thin film of water has defined Earth's character. It has shaped our geology, driving erosion and weathering, creating sedimentary rocks, lubricating plate tectonics. It has moderated our climate, absorbing and redistributing heat, buffering temperature changes, and most importantly, it has made life possible, providing the medium in which chemistry became biology, the environment in which life evolved and diversified. Water is precious not because it's abundant, Earth is mostly rock, but because it's present at all, because it exists in liquid form on the surface, because conditions here allow it to cycle between ice, liquid, and vapor. That 0.05% of Earth's mass is the most important 0.05%, the fraction that makes our planet unique among all the worlds we've discovered. We live on a water world, but only barely. We're a rocky planet with a water coating, and that coating is thinner than we often realize. Neptune's moon Triton orbits backward. While Neptune rotates in one direction, Triton circles it in the opposite direction, what's called a retrograde orbit. This is extremely unusual for large moons, which typically orbit in the same direction as their planet's rotation. A retrograde orbit suggests Triton wasn't born alongside Neptune. Instead, Triton was probably a separate object, perhaps a dwarf planet similar to Pluto, that wandered too close to Neptune and was gravitationally captured. The capture process would have been violent, possibly involving collisions with other moons or complex gravitational interactions that bled away Triton's orbital energy until it was trapped in Neptune's gravity well. But retrograde orbits are unstable over very long timescales. Tidal forces between Neptune and Triton are causing Triton to slowly spiral inward, getting closer to Neptune with each orbit. Eventually, in about 3.6 billion years, Triton will cross what's called the Roche limit, the distance at which Neptune's tidal forces will overcome Triton's own gravity. When that happens, Triton will be torn apart. The moon will fragment into billions of pieces, spreading out around Neptune to form a spectacular ring system, possibly even more impressive than Saturn's rings. Triton's fate is sealed. It's doomed by its retrograde orbit, slowly falling toward Neptune, counting down the eons until it's destroyed. For now, Triton survives, the seventh largest moon in the solar system, orbiting backward around its adopted planet, marking time until the day it's ripped to pieces by the very world it orbits. Jupiter has rings, though most people don't know about them. They're nothing like Saturn's spectacular ice rings. Jupiter's rings are faint, tenuous, made mostly of dust rather than ice. You can't see them with a small telescope. They're so thin and dark that they were only discovered when Voyager 1 flew past Jupiter in 1979 and photographed them backlit by the sun. These rings are created by micrometeorite impacts on Jupiter's inner moons. When a tiny space rock strikes one of these moons at high velocity, it kicks up a spray of dust. that dust enters orbit around Jupiter, slowly spiraling outward or inward, creating diffuse rings of material. The main ring is about 4,000 miles wide but less than 20 miles thick. A disk of dust particles so sparse that if you flew through it, you probably wouldn't even notice. There are also gossamer rings extending from some of Jupiter's small moons, even fainter, even more ephemeral. Jupiter's rings are constantly being created and constantly dissipating. The dust particles are small enough to be affected by Jupiter's magnetic field and solar radiation pressure, which gradually clear them away. But new dust is constantly being added by ongoing impacts on the moons. The rings persist in a steady state, not permanent structures like Saturn's rings, but transient features maintained by ongoing processes. They're ghost rings, barely there, invisible to most observers, a secret that Jupiter keeps hidden until you know exactly where to look and how to see them. Venus has a peculiar relationship with Earth. Its orbit is configured such that every time Venus and Earth come closest to each other, what's called inferior conjunction, Venus presents nearly the same face toward Earth. It's not a perfect lock, but Venus rotates almost exactly 5 times for every 8 Earth years. And this creates a pattern where the same side of Venus tends to face Earth at each close approach. This is called a resonance, though whether it's a genuine gravitational lock or just a coincidence is still debated. Some scientists think Earth's gravity has influenced Venus's rotation over billions of years, gradually slowing it and locking it into this pattern. Others think it's just statistical chance, a near resonance that happens to exist now but might drift over millions of years. Either way, it means that every 584 days, when Venus and Earth reach their closest approach, Venus has rotated such that nearly the same hemisphere faces us. If you could see through Venus's clouds and map its surface features, you'd notice this pattern, the same mountains and valleys oriented toward Earth at each conjunction. It's as if Venus is showing us its face repeatedly, maintaining eye contact across millions of miles of space. Whether this is gravitational choreography or cosmic coincidence, it creates an eerie connection between our world and our toxic sister planet, a dance of rotation and orbit that's been playing out for millions of years. Venus keeps presenting the same face to Earth, over and over, as if it has something to show us beneath those impenetrable clouds. Uranus was the first planet discovered in modern times, expanding humanity's known solar system beyond the 5 planets visible to the naked eye. On March 13th, 1781, William Herschel, an amateur astronomer in Bath, England, was conducting a systematic survey of the stars when he noticed an object that didn't look quite right. It wasn't a point of light like the stars. It showed a disk, barely perceptible but definitely not stellar. Herschel initially thought it might be a comet, but as he tracked it over several nights, he realized it was moving in a nearly circular orbit far beyond Saturn. It was a planet, an entirely new world that nobody had known existed. For thousands of years, humanity had known 5 planets: Mercury, Venus, Mars, Jupiter, and Saturn. These were the wandering stars, the lights that moved against the fixed background of the constellations. They were fundamental to ancient astronomy, astrology, timekeeping, mythology. And then suddenly, Herschel doubled the number of known planets overnight. The discovery of Uranus changed how we thought about the solar system. If there was one unknown planet, might there be others? It sparked a search that eventually led to the discovery of Neptune, and later the asteroids, and eventually Pluto. It opened up the possibility that the solar system was larger and more complex than anyone had imagined. Herschel wanted to name the planet Georgium Sidus, George's star, after King George III, but eventually it was named Uranus, continuing the tradition of naming planets after classical deities. And the solar system was never the same again. Mars has 2 tiny moons, Phobos and Deimos, named after the Greek gods of fear and panic who accompanied Ares, the god of war, Mars in Roman mythology. They're small, irregularly shaped, and probably aren't moons in the traditional sense. They're most likely captured asteroids that wandered too close to Mars and fell into orbit. Phobos is the larger of the two, measuring about 17 miles across at its widest point. It's heavily cratered and marked by strange grooves that might have been caused by tidal stresses from orbiting so close to Mars. Phobos orbits just 3,700 miles above Mars's surface, closer than any other known moon orbits its planet. At this distance, it completes an orbit in only 7 hours and 39 minutes, faster than Mars rotates. This creates a bizarre situation. From Mars's surface, you can watch Phobos rise in the west and set in the east, opposite to the Sun and stars, and because Phobos orbits so close, it looks large in the Martian sky. About half the size of our moon appears from Earth. You'd see Phobos race across the sky, rising and setting more than 3 times per Martian day. Deimos is smaller and farther out, orbiting just beyond Mars's synchronous orbit distance. It rises in the east and sets in the west like normal, but it moves so slowly that it stays in the sky for more than 2 Martian days before setting. These moons are oddities, irregular chunks of rock, probably visitors from the asteroid belt captured by Mars's gravity billions of years ago and held there ever since, doomed companions to the red planet. Earth is the only planet where water exists naturally in all 3 states, solid, liquid, and gas on its surface. Ice at the poles and on mountains, liquid water in the oceans and lakes and rivers, and water vapor in the atmosphere. This triple point existence is crucial to Earth's weather, its geology, and the chemistry of life. The water cycle depends on these phase transitions. Water evaporates from the oceans, rising into the atmosphere as vapor. It condenses into clouds, forming liquid droplets. These droplets grow and fall as rain, and running across the land, dissolving minerals, carving valleys, returning eventually to the sea. In colder regions, water freezes into snow and ice, storing it for seasons or years or millennia before melting and rejoining the cycle. No other planet in the solar system has this. Mars has water ice at the poles and possibly subsurface liquid, but not surface liquid. Europa and Enceladus have subsurface oceans, but their surfaces are frozen solid. Venus's surface is far too hot for any form of water to exist. It's all vapor in the atmosphere. The gas giants have water vapor and possibly liquid or ice in their interiors, but no surface at all. Earth's unique position, not too close to the Sun, not too far away, allows water to exist in all 3 forms at surface pressure and temperature. And this triple point behavior makes Earth dynamic in ways other worlds aren't. Water moves between states, transports energy and matter, shapes the landscape, and creates the conditions where life can emerge and thrive. We live on a world of transformations, where water is always changing, always moving, never still. Saturn's density is so remarkably low that it would float in water if you could find a bathtub large enough. At 0.687 grams per cubic centimetre, Saturn is less dense than water, which has a density of 1.0 grams per cubic centimetre. It's even less dense than some types of wood. Balsa wood has a density of about 0.16 grams per cubic centimetre, so Saturn wouldn't float quite as high as balsa, but it would still bob on the surface. Of course, this is a thought experiment. There's no ocean large enough to hold Saturn, and even if there were, Saturn would likely dissolve or react chemically with the water in spectacular ways. But the calculation holds. Saturn is so light for its size that it will displace more mass in water than it weighs. This extremely low density comes from Saturn's composition. It's made almost entirely of hydrogen and helium, the two lightest elements in the universe. There's a rocky core deep inside, but it's tiny compared to the planet's overall volume. Most of Saturn is just gas, compressed by gravity into a massive sphere but still fundamentally lightweight. It's almost absurd to think about. This enormous planet, 95 times more massive than Earth, with spectacular rings and dozens of moons, this giant that dominates its region of space, it's mostly empty. It's hydrogen and helium compressed into a planet-sized volume but still lighter, gram for gram, than the water in your glass. Saturn is a cosmic balloon, and if you could somehow test it, it would float. Neptune was discovered through mathematics before it was seen through a telescope. By the 1840s, astronomers had been tracking Uranus for decades, carefully measuring its position against the background stars. But Uranus wasn't moving exactly as Newton's laws predicted. Its orbit showed small but measurable deviations, perturbations that suggested something massive was pulling on it gravitationally. Two mathematicians working independently, John Couch Adams in England and Urbain Le Verrier in France, set out to find the invisible planet. They assumed there was an eighth planet beyond Uranus, and used the perturbations in Uranus's orbit to calculate where that planet should be. It was extraordinarily difficult mathematics, solving for the position, mass and orbit of an unseen object based only on its gravitational influence. Le Verrier completed his calculations first and sent them to Johann Galle at the Berlin Observatory. On September 23, 1846, Galle pointed his telescope to the predicted position and found Neptune, almost exactly where Le Verrier had said it would be, within 1 degree of the calculated position. It was a triumph of theoretical astronomy, proof that mathematics could reveal truths invisible to observation. Neptune existed as a set of equations before it existed as a visible object, a found not by sweeping the sky with telescopes, but by following the logic of gravity to its inevitable conclusion. Sometimes you don't need to see something to know it's there. Sometimes the universe leaves clues, tiny wobbles, small deviations, and if you follow those clues carefully enough, they lead you exactly where you need to look. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, were discovered by Galileo Galilei in January 1610, just weeks after he turned his newly improved telescope toward the night sky. These discoveries were revolutionary, and not just for astronomy. They provided some of the first observational evidence that not everything in the universe orbited Earth. At the time, the prevailing cosmological model held that Earth was the center of everything: the sun, moon, planets, and stars all revolved around us. But Galileo watched these 4 points of light moving around Jupiter night after night, clearly orbiting the giant planet rather than Earth. Here was proof that some celestial objects had their own satellites, their own centers of motion. This observation didn't prove the heliocentric model by itself, but it undermined the geocentric worldview. If moons could orbit Jupiter, then perhaps Earth wasn't the universal centre after all. Perhaps planets, including Earth, could orbit the Sun. The idea was dangerous enough that Galileo eventually faced trial by the Inquisition and spent his final years under house arrest. Those 4 moons, now called the Galilean satellites, are worlds in their own right. Io spews sulfur from hundreds of volcanoes. Europa hides a subsurface ocean. Ganymede is larger than Mercury and generates its own magnetic field. Callisto is ancient and heavily cratered, a fossil record of the early solar system. Each is unique, each is fascinating, and together they changed how humanity understood its place in the cosmos. 4 tiny points of light orbiting Jupiter helped overturn thousands of years of certainty about Earth's central position in the universe. Mercury's orbit is slowly decaying, gradually becoming more eccentric and chaotic over millions of years. Computer simulations of the solar system's long-term evolution show that Mercury's orbit is unstable on timescales of billions of years. In about 5 billion years, around the same time the Sun begins to die, there's a small but real chance that Mercury could either collide with Venus, collide with Earth, or fall into the Sun. The probability isn't high, maybe 1% or less, but it's not zero either. Mercury's orbit is influenced by gravitational perturbations from all the other planets, particularly Venus and Jupiter. Over billions of years, these tiny tugs accumulate, and orbital mechanics become chaotic. Small changes in initial conditions can lead to wildly different outcomes. In some simulations, Mercury's orbit remains stable. In others, it spirals inward toward the Sun. In still others, it gets ejected from the inner solar system entirely, or collides with another planet. This reminds us that the solar system's current configuration isn't permanent. The orbits we see now, the neat arrangement of planets marching around the Sun in stable paths, won't last forever. Over truly vast timescales, billions of years, orbital chaos creeps in. Gravitational interactions that seem negligible now accumulate into significant changes. Mercury is the most vulnerable, the most likely to be disrupted. Its small mass and proximity to the Sun make it susceptible to perturbations. The innermost planet's fate is genuinely uncertain, written in probabilities and chaotic dynamics rather than deterministic certainty. The solar system has a future, and that future might not include Mercury. Mars once had rivers. We can still see them. Dried riverbeds carved into the Martian surface, winding channels that once carried flowing water, deltas where rivers emptied into ancient lakes or seas. Some of these features are billions of years old, formed when Mars had a thicker atmosphere and warmer temperatures. The evidence is everywhere once you know what to look for. Orbital images show dendritic patterns, branching networks of channels that look exactly like river systems on Earth, carved by water flowing downhill. There are features that look like alluvial fans, where rivers deposited sediment as they slowed. There are ancient lake beds with terraced shorelines marking different water levels over time. Some scientists think Mars may have once had a northern ocean covering much of the low-lying northern hemisphere. The evidence is circumstantial but compelling. A smooth, flat plain at consistent elevation that could have been an ocean floor, possible ancient coastlines, and channels that seem to have flowed into this region. But all of this was billions of years ago, back when Mars still had its magnetic field, before the solar wind stripped away most of the atmosphere. As the air thinned and temperatures dropped, the water disappeared. Some froze into the polar ice caps or became locked in subsurface ice. Some evaporated and was lost to space. The rivers stopped flowing, the lakes dried up, and Mars became the frozen desert we see today. Those ancient riverbeds remain, though, ghostly traces of a wetter past, channels carved by water that hasn't flowed in billions of years, monuments to a Mars that might have been habitable. Earth's magnetic field wanders and occasionally flips completely. The North Magnetic Pole isn't fixed in place. It drifts, moving several miles per year, currently migrating from northern Canada towards Siberia. This wandering is caused by changes in the flow of liquid iron in Earth's outer core, the dynamo that generates our magnetic field. But sometimes, the field doesn't just wander, it reverses entirely. The north and south magnetic poles swap positions in what's called a geomagnetic reversal. We know this happens because volcanic rocks preserve a record of Earth's magnetic field direction when they solidify. By studying rocks of different ages, we can map out the history of these reversals. They're not regular or predictable. Sometimes millions of years pass between reversals, sometimes only tens of thousands of years. The last reversal occurred about 780,000 years ago, the Brunhes-Matuyama reversal, and there's some evidence we might be overdue for the next one. The magnetic field has been weakening over the past few centuries, which could be an early sign of an impending flip, though it's impossible to say for certain. During a reversal, which takes thousands of years to complete, the magnetic field weakens significantly and becomes more complex, possibly splitting into multiple poles. This could increase radiation exposure at the surface and disrupt navigation systems and power grids. Life has survived many reversals before, but it would certainly be disruptive to modern technological civilization. Earth's magnetic shield isn't stable. It shifts, weakens, and occasionally flips, driven by the churning metal ocean miles beneath our feet, following patterns we still don't fully understand. Uranus appears blue-green in photographs, a serene cyan colour that makes it look like a frozen marble suspended in darkness. This colour comes from methane in the upper atmosphere. Methane molecules absorb red light very efficiently, but reflect blue and green wavelengths back into space, giving Uranus its distinctive colour. Yeah, but Uranus's colour is subtler, more muted than Neptune's deeper blue. Both planets have similar amounts of methane in their atmospheres, yet Neptune appears more vividly coloured. Scientists think there might be an additional unknown component in Neptune's atmosphere that enhances its blue colour, or perhaps subtle differences in atmospheric structure create the different appearances. Uranus itself is relatively featureless when observed in visible light. Unlike Jupiter and Saturn with their prominent bands and storms, or even Neptune with its dark spots and bright clouds, Uranus appears as a nearly uniform pale cyan disk. The Voyager 2 images from 1986 showed almost no cloud features at all, leading scientists to call it the bland planet. But more recent observations with improved instruments have revealed that Uranus does have atmospheric features. They're just very faint and difficult to see. There are subtle bands, occasional bright clouds, and possibly storm systems. They're just much less pronounced than on the other giant planets, hidden beneath that featureless cyan appearance. Uranus keeps its weather to itself, presenting a calm, almost serene face to observers, while whatever storms and winds exist on that tilted world remain largely invisible beneath layers of methane-tinted haze. Venus has been visited by more spacecraft than any other planet besides Earth. the Soviet Union sent a series of Venera probes beginning in the 1960s, attempting to land on and explore the hostile Venusian surface. Many failed and destroyed by the crushing pressure and searing heat before they could transmit data. But some succeeded, becoming the first, and still among the very few, spacecraft to send back images and measurements from the surface of another planet. The longest surviving lander was Venera 13, which touched down on March 1st, 1982. It operated for 127 minutes, just over 2 hours, before the heat and pressure destroyed it. In that brief window, it transmitted colour images of the surface, analysed soil samples, and measured atmospheric conditions. The images show a landscape of flat rocks under an orange sky, illuminated by sunlight filtered through the thick atmosphere. 127 minutes. That's all the time Venera 13 had to work before the 900-degree heat melted its electronics and the crushing 92 atmosphere pressure finished the job. But in those minutes, it captured data that remains unique. Direct measurements from the surface of Venus, a place so hostile that even heavily armoured robots can only survive briefly. Other nations have sent orbiters to study Venus from above, and there have been a few landers since, but the Soviet Venera missions remain remarkable achievements. They showed that even the most hellish environment in the solar system can be visited, if only briefly, before the planet claims another victim. Venus has destroyed more spacecraft than it has allowed to survive, jealously guarding its secrets beneath those toxic clouds. Jupiter's moon, Io, is the most volcanically active body in the solar system. It has hundreds of active volcanoes erupting almost constantly, spewing sulfur and sulfur dioxide plumes that can reach hundreds of miles into space. The surface is constantly being resurfaced by lava flows, burying impact craters almost as fast as they form, giving Io the youngest surface of any solid body in the solar system. This extreme volcanism comes from tidal heating. Io orbits Jupiter in a slightly elliptical orbit, and as it moves closer and farther from the giant planet, Jupiter's gravity squeezes and stretches Io like a stress ball. This constant flexing generates enormous amounts of heat through friction, enough heat to keep Io's interior molten and drive continuous volcanic activity. Io pumps out more heat than all of Earth's volcanoes combined. Its surface is covered in sulfur compounds, yellow, red, orange, white, creating a landscape that looks more like a pizza or a diseased egg than a typical moon. There are lava lakes that never cool, calderas dozens of miles across, and volcanic plumes that erupt continuously for years. When Voyager 1 first photographed Io in 1979 and saw those erupting volcanoes, it was a shock. Nobody expected to find active volcanism on a moon, but Io has been erupting for billions of years, constantly reshaping its surface, driven by the relentless tidal forces of orbiting so close to Jupiter. Io is a tortured world, perpetually squeezed by gravity, its interior never allowed to rest, volcanoes erupting endlessly under the pale light of distant Jupiter. Saturn has a mysterious hexagonal cloud pattern at its north pole that's been stable for at least 4 decades, longer than we've been able to observe it. Each side of this hexagon is about 9,000 miles long, making the entire structure wider than 2 Earths, and it rotates as a coherent shape with a period of 10 hours and 39 minutes, which matches Saturn's internal rotation rate. Scientists have recreated hexagonal vortices in laboratory experiments by rotating fluids at specific speeds with particular temperature gradients. This suggests the hexagon is some kind of standing wave pattern in Saturn's atmosphere, maintained by the interaction between jet streams at different latitudes, but nobody fully understands why it forms a hexagon specifically, rather than some other polygon or an irregular shape. The hexagon isn't just a cloud pattern on the surface, it extends deep into Saturn's atmosphere, at least 60 miles down. It's a column of rotating atmosphere, hexagonal in cross-section, spinning with the planet. Inside the hexagon is a massive vortex. Yeah, an eye-like structure similar to the eye of a hurricane, surrounded by the six-sided wall of clouds. Recent observations have shown that the hexagon changes colour with Saturn's seasons, shifting from golden brown to more bluish hues as sunlight conditions change. But the shape remains. 6 straight sides meeting at angles, a geometric pattern persisting in the chaos of a gas giant's atmosphere, stable for decades, possibly for centuries. It's one of the strangest features in the solar system. A shape that looks designed, mathematical, almost artificial, yet created entirely by natural atmospheric processes we're still struggling to fully explain. All the planets orbit the Sun in the same direction, counterclockwise when viewed from above the Sun's north pole. This isn't a coincidence, it's a memory of the solar nebula's rotation, the spinning cloud of gas and dust from which all the planets formed 4.6 billion years ago. When that cloud began to collapse under its own gravity, it was already rotating slightly. As it collapsed, it spun faster, the same way an ice skater spins faster when pulling their arms in. This rotation caused the cloud to flatten into a disk, with the proto-sun forming at the centre and planets condensing from the surrounding material. Because everything formed from the same rotating disk, everything inherited that rotation. The planets all orbit in the same direction, in roughly the same plane, preserving the angular momentum of the original cloud. It's a fossil in a sense, a trace of the solar system's birth frozen into the architecture of planetary orbits. Venus rotates backward on its axis, probably due to a collision or tidal effects, and Uranus rotates on its side, also likely from an impact, but their orbits around the Sun still follow the original pattern, still counterclockwise, still in the same plane. When you look at the solar system's flat disk structure, when you notice all the planets circling the Sun in the same direction, you're seeing an echo of a spinning cloud that collapsed 4.6 billion years ago. The solar system remembers how it was born, written in orbital mechanics, preserved in the synchronized dance of worlds around the Sun. Neptune has 14 known moons, but one of them, Triton, dominates completely. Triton contains about 99.5% of all the mass-orbiting Neptune. The other 13 moons are essentially just accompanying debris, tiny rocks and captured objects that pale in comparison to Triton's bulk. Triton itself is fascinating. It's the 7th largest moon in the solar system, larger than Pluto, with a diameter of about 1,680 miles. Its surface is young and geologically active, marked by cryovolcanoes that erupt nitrogen geysers. It has a thin atmosphere of nitrogen and methane, and most unusually it orbits Neptune backward, retrograde, suggesting it was captured rather than formed alongside the planet. The other moons are much smaller. Proteus, the second largest, is only about 260 miles across. Nereid has a highly eccentric orbit that takes it from very close to Neptune to far away. The rest are even smaller, some only a few miles in diameter. probably captured asteroids or fragments from larger moons that were destroyed in collisions. Triton's dominance means Neptune's satellite system is fundamentally lopsided. There's one large moon and a collection of minor satellites, unlike Jupiter and Saturn, which have multiple large moons. This asymmetry probably results from Triton's capture. When it was pulled into orbit around Neptune, its gravitational influence likely disrupted Neptune's original moon system, causing collisions and ejections that left only small fragments in addition to Triton itself. Neptune's moons tell a story of catastrophe, a large object captured, an original system destroyed, and only Triton and debris remaining in the aftermath. Mercury has enormous cliffs called scarps that stretch for hundreds of miles across its surface. Some rise nearly 2 miles high, massive wrinkles in the planet's crust, like the skin of a drying apple. These scarps formed as Mercury cooled and contracted over billions of years, its interior shrinking as heat radiated away into space. As the core and mantle cooled, they took up less volume. The surface crust, already solidified, had to adjust to accommodate this shrinking interior. It buckled and folded, creating these enormous thrust faults, where one section of crust was pushed up and over another. The scarps are essentially wrinkles frozen into the landscape, permanent creases created by the slow contraction of an entire planet. Some of these scarps cut through craters, showing that they formed after the craters did. Others are themselves cratered, showing their ancient features that have been around for billions of years. Mercury has probably shrunk by about 7 miles in radius since it formed. Not much in absolute terms, but enough to create these dramatic surface features. Other planets don't show this kind of global contraction. Earth's interior is still hot enough to drive plate tectonics, constantly reshaping the surface. Mars and the Moon show some evidence of early contraction, but nothing as pronounced as Mercury. Mercury is unique in how dramatically it has wrinkled, its surface preserving a record of billions of years of slow cooling. When you look at Mercury's scarps, you're seeing the face of a planet that's shrinking, gradually collapsing inward as its ancient heat escapes, creating a landscape of frozen wrinkles that will persist for billions more years. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, and other gases. This composition is highly unusual for rocky planets. Venus and Mars both have atmospheres dominated by carbon dioxide. The gas giants have atmospheres of hydrogen and helium, but Earth's air is mostly nitrogen, and that 21% oxygen is almost entirely the product of life. Oxygen is reactive. It wants to combine with other elements, rusting iron, burning wood, supporting combustion and respiration. Free molecular oxygen shouldn't exist in any significant quantity in a planet's atmosphere, because it would quickly react with surface materials and disappear. The fact that Earth's atmosphere contains so much oxygen is direct evidence that something is constantly producing it. That something is photosynthesis. Plants, algae, and cyanobacteria use sunlight to convert carbon dioxide and water into sugars and oxygen. They've been doing this for billions of years. Cyanobacteria began producing oxygen at least 2.4 billion years ago, gradually transforming Earth's atmosphere from carbon dioxide rich to oxygen rich. This means Earth's atmosphere is fundamentally a product of biology. The air you're breathing right now was created by life. Every breath you take contains oxygen molecules that were manufactured by photosynthetic organisms, possibly just hours or days ago. possibly halfway around the world, released into the atmosphere and carried by winds to wherever you are now. Our atmosphere isn't primarily a geological feature, it's biological. Life created the air we breathe, and life continuously maintains it, replacing the oxygen that gets consumed by respiration and decay and chemical reactions. Mars's Olympus Mons grew to become the tallest mountain in the solar system because Mars lacks plate tectonics. On Earth, and the crust is divided into plates that slowly move across the surface. When a volcano forms over a hotspot, a plume of hot material rising from deep in the mantle, the plate gradually carries the volcano away from its magma source. This creates chains of volcanoes, like the Hawaiian Islands, each one forming over the hotspot and then drifting away as the plate moves. But on Mars, the crust doesn't move. There are no plates, no tectonic drift. When a volcano forms over a magma source, it stays there, erupting again and again, building higher and higher for hundreds of millions of years. Olympus Mons had the same eruption site for an immense span of time, allowing it to grow into a mountain 72,000 feet tall and 374 miles across. Earth's tallest volcano, Mauna Kea in Hawaii, is about 33,500 feet from its base on the ocean floor to its peak, less than half the height of Olympus Mons, and Mauna Kea is already drifting away from its hotspot, slowly moving northwest as the Pacific Plate carries it. Eventually it will become extinct, its magma source left behind, and a new volcano will form in its place. Mars's geological stillness, its lack of plate movement, allowed Olympus Mons to become a monument to billions of years of volcanic activity. It's a mountain built layer by layer, eruption by eruption, growing taller because nothing moved it away from the fire beneath. Jupiter's gravity has prevented the asteroid belt from forming a planet. In the early solar system, the asteroid belt region contained rocky material that should have accumulated into a planet just like the material closer to the Sun formed Mercury, Venus, Earth, and Mars. But Jupiter's massive gravitational influence stirred up the asteroids, increasing their orbital velocities and collision speeds. When asteroids collided at low speeds, they could stick together, gradually accumulating into larger bodies. But when Jupiter's gravity increased their velocities, collisions became more violent. Instead of merging, asteroids began to shatter when they hit each other, breaking apart rather than building up. Jupiter effectively prevented planet formation in the asteroid belt by making the collisions too destructive. There's evidence that the asteroid belt once contained much more material than it does now. Jupiter's gravity also ejected many asteroids from the belt entirely, scattering them throughout the inner and outer solar system or sending them into the Sun. The asteroid belt we see today is just the remnant of a much more massive disk of material. If Jupiter hadn't existed, or if it had formed farther from the Sun, the asteroid belt might have accumulated into a planet, probably something Mars-sized or larger, orbiting between Mars and Jupiter. Instead, we have a scattered field of rubble, millions of objects ranging from dust grains to Ceres, none of them able to complete the process of planetary formation. Jupiter's gravity has shaped the solar system's architecture, determining not just where planets formed, but also where they couldn't form, creating gaps and structure through its sheer gravitational dominance. Venus's surface is geologically young, only about 300 to 600 million years old. This might not sound young in human terms, but for a planet that's 4.5 billion years old, it means the surface is less than 15% as old as the planet itself. The the surface was completely renewed in a relatively recent geological event, burying everything that came before under fresh lava. We know this because Venus has very few impact craters. If the surface were ancient, it should be heavily cratered like the Moon or Mercury, recording billions of years of asteroid and comet impacts. But Venus's surface is remarkably smooth and crater-poor, suggesting it was resurfaced, and that craters have only been accumulating since then. The leading theory is that Venus underwent a catastrophic global resurfacing event. Perhaps the planet's interior heat built up over billions of years because Venus lacks plate tectonics, no mechanism to release heat gradually. Eventually the heat became too much, and the entire crust foundered, ice sinking into the mantle while massive amounts of lava erupted across the entire planet, covering the old surface completely. This might have been a one-time event, or it might happen periodically every few 100 million years. We don't know if it will happen again. Venus might be geologically active right now, building up toward another global resurfacing, or it might have settled into dormancy. The surface we see today is the product of that catastrophe, a global lava flow that buried Venus's ancient history, leaving only a relatively young, uniform surface scarred by volcanoes and lava channels. Uranus radiates almost no excess heat, unlike the other giant planets. Jupiter, Saturn, and Neptune all emit significantly more energy than they receive from the Sun. They're still warm from their formation billions of years ago, still radiating away that primordial heat. But Uranus emits only about as much energy as it absorbs from the Sun. Its internal heat source is mysteriously absent or inaccessible. Scientists believe the massive impact that knocked Uranus on its side may have also disrupted the planet's internal heat flow. Perhaps the collision allowed much of Uranus's internal heat to escape suddenly, leaving the planet unusually cold inside. Or perhaps the impact scrambled Uranus's interior structure, creating layers that prevent heat from rising to the surface efficiently. Whatever the reason, Uranus is anomalously cold for a giant planet. Its upper atmosphere is the coldest in the solar system, and the planet shows less weather activity than Neptune despite being closer to the Sun. Neptune, farther from the Sun and receiving less solar energy, has faster winds and more prominent storms because its internal heat drives atmospheric circulation. Uranus, lacking that internal heat, is relatively quiet. This makes Uranus a broken planet in multiple ways. It's knocked on its side, robbed of its internal warmth, spinning through space colder and quieter than it should be. The impact that tilted Uranus didn't just change its orientation, it may have fundamentally altered its internal structure and evolution. Uranus stands as evidence that a single catastrophic event can reshape a planet's entire character for billions of years. Saturn's rings cast shadows on the planet's surface, creating dark bands that move across Saturn's clouds as the planet rotates and the angle of sunlight changes. These shadows are most dramatic near Saturn's equinoxes, the times when the Sun crosses Saturn's equatorial plane and the rings appear edge onto the Sun. During equinox, which occurs about every 15 years as Saturn orbits the Sun, the rings cast their thinnest shadows, creating precise dark lines across the planet. At other times, when the rings are tilted relative to the Sun, the shadows are broader and more diffuse, but they're always there, silent witnesses to the ring's presence painted in darkness across the clouds. From Saturn's surface, if there were a surface to stand on, the rings would be spectacular. They would arc across the sky from horizon to horizon, impossibly thin, brilliantly bright, dominating the view. And twice per Saturn day, the rings would cast shadows, these creating periods of partial eclipse as the ring shadow swept across your location. These shadows affect Saturn's weather. They block sunlight, cooling the atmosphere beneath them, potentially creating temperature gradients that drive winds and cloud formation. The rings don't just beautify Saturn, they actively influence its climate and atmospheric dynamics. Every 15 years, as Saturn reaches equinox, the rings become almost invisible from Earth, appearing as just a thin line of light. During these times, the shadows they cast on Saturn are also at their most subtle, but the shadows always return as the orbital geometry shifts, marking time on a planet of clouds and storms. Earth's rotation is gradually slowing down due to tidal interactions with the Moon. The Moon's gravity raises tides in Earth's oceans, and as Earth rotates beneath these tidal bulges, friction between the moving water and the ocean floor transfers angular momentum from Earth's rotation to the Moon's orbit. The effect is tiny but measurable. Days are getting longer by about 1.8 milliseconds per century. Over human timescales, this is completely negligible. You'd never notice the difference. But over geological time, it adds up significantly. About 620 million years ago, during the Ediacaran period, a day lasted only about 21.9 hours. There were more days in a year, perhaps 400 or so, because the year's length is determined by Earth's orbit, which isn't significantly affected by tidal friction. Ancient corals and other organisms that grew in daily and annual cycles preserve evidence of this in their growth patterns. Going back even further to the early Earth, yes, days may have been only 6 to 10 hours long. The Moon was much closer then, possibly only 15,000 miles away compared to today's 238,000 miles, and tidal forces were correspondingly stronger. As Earth's rotation slows, the Moon gradually recedes, moving about 1.5 inches farther from Earth each year. The two are locked in a dance where Earth spins down and the Moon spirals outward, conserving the total angular momentum of the system. Eventually, billions of years from now, Earth's rotation will slow enough that one side will perpetually face the Moon, just as the Moon already keeps one face toward Earth. The day and month will have the same length, and both Earth and Moon will be tidally locked to each other. Neptune's atmosphere contains traces of a mysterious dark material that absorbs light more strongly than methane alone would, contributing to the planet's deep blue colour beyond what pure methane absorption would produce. Scientists have been trying to identify this unknown substance for decades. Spectroscopic observations show that Neptune's colour can't be fully explained by methane. There's something else there, some additional absorber that's particularly effective at removing red light from the spectrum, but identifying exactly what it is has proven difficult. Recent research suggests it might be a photochemical haze, complex organic molecules formed when ultraviolet light from the sun breaks apart methane molecules high in the atmosphere. These fragments recombine into larger molecules, possibly including compounds like acetylene, ethylene, and more complex hydrocarbons. These haze particles could selectively absorb red light, deepening Neptune's blue colour, or it might involve some combination of methane ice crystals, hydrogen sulfide, or other minor atmospheric components interacting in ways that enhance the absorption. The answer likely involves multiple factors working together rather than a single mystery molecule. Neptune's exact shade of blue, that intense azure that makes it appear darker and more saturated than Uranus, despite similar methane content, remains slightly mysterious. We can see the colour clearly, we can measure it spectroscopically, but we can't fully account for it with known atmospheric components alone. Neptune keeps some secrets, even obvious ones like, why exactly are you that particular shade of blue? Mercury has a peculiar orbit that doesn't quite follow Newton's laws of gravity. The perihelion of Mercury's orbit, the point where it's closest to the Sun, precesses, or shifts, by about 574 arcseconds per century. Newton's laws, accounting for the gravitational influence of all the other planets, could explain about 531 arcseconds of this precession. But there were 43 arcseconds per century that remained unexplained. For decades, this tiny discrepancy puzzled astronomers. Some proposed the existence of another planet closer to the Sun than Mercury. They even named it Vulcan, but searchers never found it. Others suggested modifications to Newton's laws or invisible matter affecting Mercury's orbit. Then in 1915, Albert Einstein published his general theory of relativity, which describes gravity not as a force but as a curvature of space-time. When Einstein's equations were applied to Mercury's orbit, they naturally predicted the additional 43 arcseconds of precession without requiring any modifications or hidden planets. The excess precession was a consequence of space-time curvature near the Sun, a relativistic effect too small to notice for more distant planets, but just barely detectable for Mercury. This was one of the first confirmations that Einstein's theory was more accurate than Newton's, that gravity worked differently than we'd thought for 3 centuries. A tiny wobble in Mercury's orbit, less than 43 arcseconds per century, was enough to reveal that space-time itself was curved. Mercury, the smallest planet, orbiting in the strongest gravitational field, showed us that the universe follows rules stranger and more subtle than Newton imagined. Mars's 2 small moons are doomed. Phobos, the larger and closer of the two, theirs is slowly spiralling inward toward Mars, getting about 6 feet closer every century. This doesn't sound like much, but over millions of years it adds up. In about 50 million years, Phobos will either crash into Mars's surface or, more likely, be torn apart by tidal forces before it gets that far. When Phobos crosses the Roche limit, the distance at which Mars's tidal forces will overcome the Moon's own gravity, it will fragment into billions of pieces. These pieces will spread out around Mars, forming a ring system similar to Saturn's rings, though probably much less spectacular and much more temporary. Mars will have rings for perhaps tens of millions of years before the debris either falls to the surface or disperses. Deimos, the smaller and more distant moon, faces a different fate. It's slowly drifting away from Mars, and is gaining orbital energy through tidal interactions. Eventually, in perhaps a few billion years, Deimos will drift far enough that it either escapes Mars's gravity entirely or settles into a stable distant orbit. Either way, Mars will lose its companion, so Mars's moons are temporary. Phobos is falling, doomed to destruction within a cosmically brief time span. Deimos is drifting away, slowly leaving its planet behind. In perhaps 100 million years, Mars might be moonless, or it might have a temporary ring system made from Phobos's shattered remains, or it might have only distant Deimos still hanging on. The Martian moon system is dissolving, pulled apart by the same tidal forces that created our moon's recession from Earth, but playing out much faster on these small close satellites. Jupiter could have become a star if it had been about 80 times more massive than it is. Stars form when a collapsing cloud of gas becomes dense and hot enough at its core to ignite nuclear fusion, hydrogen atoms fusing into helium, releasing enormous amounts of energy. This requires a minimum mass of about 80 Jupiter masses, though there's some variation depending on composition. Jupiter is massive, more than twice the mass of all the other planets combined, but it's still only about 0.1% of the Sun's mass, and only about 1/80,000th of the mass needed to become a star. It fell short by a factor of roughly 75. If the early solar system had contained more material in Jupiter's region, or if Jupiter had migrated inward and accreted more gas before the solar nebula dispersed, it might have reached the fusion threshold. Instead, and Jupiter is what astronomers call a failed star, or more accurately a gas giant planet. It has a similar composition to a star, mostly hydrogen and helium, and it radiates more heat than it receives from the Sun, a characteristic it shares with stars. But its core is not hot enough for fusion. The pressure and temperature at Jupiter's centre are immense by planetary standards, but insufficient to ignite the nuclear reactions that power stars. If Jupiter had become a star, the solar system would be fundamentally different. We'd have a binary star system, with two stars orbiting each other. The inner planets might not have formed at all, or their orbits would be drastically different. Life on Earth, if it existed, would develop under the light of two suns, but Jupiter fell just short. It's the largest planet, the dominant world, but not quite massive enough to become a star. Venus may have been habitable billions of years ago. Climate models suggest that early Venus, shortly after its formation, could have had liquid water oceans on its surface for perhaps 2 billion years or more. During this time, Venus might have been more Earth-like than the toxic hothouse we see today. Early in the solar system's history, the Sun was about 30% dimmer than it is now. This meant Venus, despite being closer to the Sun than Earth, might have received roughly the same amount of solar radiation that Earth receives today. With liquid water and a moderate climate, early Venus could have been habitable, perhaps even home to life. But something changed. The leading theory is that Venus experienced a runaway greenhouse effect. As the Sun gradually brightened over billions of years, ice temperatures on Venus increased. This caused more water to evaporate into the atmosphere. Water vapor is a greenhouse gas, so more water vapor meant more heat was trapped, which caused even more evaporation. The feedback loop accelerated until all the water evaporated. The atmosphere became thick with water vapor and carbon dioxide, and temperatures soared. Ultraviolet radiation from the Sun then broke apart water vapor molecules, separating hydrogen from oxygen. The lightweight hydrogen escaped into space while the oxygen combined with surface rocks. Venus lost its water permanently, left with only a dense carbon dioxide atmosphere and surface temperatures hot enough to melt lead. Ancient Venus might have had blue skies, liquid oceans, and conditions suitable for life. But the runaway greenhouse effect transformed it into the hellscape we see today, a cautionary tale of how atmospheres can destabilize. The Earth's inner core rotates slightly faster than the rest of the planet, gaining about one extra rotation every 900 years or so. This phenomenon, called superrotation of the inner core, was discovered by analyzing seismic waves that travel through the Earth from earthquakes. The inner core is a solid sphere of iron about 1,500 miles in diameter, surrounded by the liquid iron outer core. Because it's surrounded by liquid, The inner core can rotate independently of the mantle and crust, and it does, driven by electromagnetic coupling with the liquid outer core, which itself is driven by Earth's rotation and convection currents. This superrotation is extremely slow. You'd never notice it directly. But over geological time, it means the inner core is making slightly more rotations than the surface. The mechanism involves complex interactions between Earth's magnetic field, the rotation of the liquid outer core, and the solid inner core's response to those forces. Recent studies have suggested the situation might be even more complex. Some evidence indicates the inner core's rotation rate might vary over time, sometimes speeding up, sometimes slowing down, possibly even briefly rotating slower than the surface. The inner core might oscillate, changing its rotation rate in cycles lasting decades. Deep inside Earth, thousands of miles beneath your feet, there's an iron ball spinning at its own rhythm, coupled to but not quite synchronized with the planet above it, following dynamics we're still working to understand fully. Saturn's moon Enceladus has geysers erupting from cracks in its south polar ice, shooting jets of water vapor and ice particles hundreds of miles into space. These plumes were discovered by the Cassini spacecraft in 2005 and represent some of the most exciting findings in planetary science. The geysers indicate that Enceladus has a subsurface ocean beneath its icy crust, and that this ocean is in contact with the surface through cracks called tiger stripes, long parallel fissures in the south polar region. The water from the deep ocean somehow reaches these cracks and erupts into space, driven by the pressure difference between the ocean and the vacuum of space. Some of this ejected material escapes Enceladus entirely and forms one of Saturn's rings, the E-ring, a faint diffuse ring of tiny ice particles. Enceladus is slowly creating a ring around Saturn through its volcanic activity, feeding material into orbit with every eruption. But the truly exciting implication is what the geysers mean for potential habitability. The plumes contain not just water, but also organic molecules, salts, and molecular hydrogen, ingredients that suggest hydrothermal activity on Enceladus's ocean floor. Hydrothermal vents, similar to those on Earth's ocean floors where entire ecosystems thrive in complete darkness, might exist on tiny Enceladus. This small moon, only about 310 miles in diameter, might harbour life in its subsurface ocean. And unlike Europa, where the ocean is sealed beneath miles of ice, Enceladus is actively venting its ocean into space, making it accessible to sampling without even needing to land. Enceladus might be one of the most promising places to search for life beyond Earth. Uranus's extreme axial tilt, 98 degrees, essentially rolling on its side, was almost certainly caused by a massive impact early in the planet's history. Something enormous, possibly an Earth-sized object or perhaps multiple large impacts, hit Uranus with enough force to knock it sideways. Computer simulations suggest that a single giant impact could have tilted Uranus and also created its moon system from the debris. Or perhaps Uranus was hit multiple times by smaller objects, each impact adding to the tilt until the planet was knocked completely over. Either way, the collision was catastrophic, fundamentally altering Uranus's orientation. This impact may have also created Uranus's faint ring system and disrupted its magnetic field. Uranus's magnetic field is oddly tilted. It doesn't align with the planet's rotation axis, and it's offset from the planet's center. This unusual configuration might be a consequence of the giant impact, which could have scrambled Uranus's interior and affected how the magnetic dynamo operates. The impact might also explain why Uranus emits so little excess heat compared to the other giant planets. Perhaps the collision allowed much of Uranus's internal heat to escape, or perhaps it disrupted the convection patterns that would normally transport heat from the interior to the surface. Uranus is a world shaped by catastrophe. The impact that knocked it on its side billions of years ago is still affecting the planet today, in its rotation, its seasons, its magnetic field, its internal heat flow. That ancient collision fundamentally changed what kind of planet Uranus would become. Neptune has completed only one full orbit around the Sun since its discovery in 1846. The planet takes 165 Earth years to make one circuit around the Sun, and it didn't return to where it was when first observed until July 12, 2011, 165 years and 287 days after Urbain Le Verrier calculated its position. Think about what that means for our understanding of Neptune. Everything we know about this planet, its atmosphere, its storms, its magnetic field, its moons, its rings, we've learned in less time than it takes to complete one orbit. We haven't observed a full seasonal cycle. We don't know what changes might occur over a complete Neptunian year. When Neptune was discovered, the United States had only 28 states. The Civil War hadn't happened yet. The light bulb hadn't been invented. Photography was in its infancy, and Neptune was beginning an orbital journey that wouldn't complete until 2011, when we had smartphones and space stations and rovers on Mars. The next time Neptune returns to this position in its orbit will be 2176. By then, our civilization will have changed in ways we can't predict. Perhaps we'll have visited Neptune directly. Perhaps we'll have settlements in the outer solar system. Perhaps we'll have discovered life on one of Neptune's moons. Or perhaps we'll have faced challenges we can't foresee. But Neptune will still be there, following the same path it's followed for billions of years, completing its patient circuit of the Sun once every 165 years, indifferent to the rise and fall of civilizations on a small blue world much closer to the light. The planets migrate. They don't stay in fixed orbits forever. Over millions of years they slowly drift inward or outward, pushed and pulled by gravitational interactions with each other and with the disk of gas and dust that filled the early solar system. Computer models suggest that Jupiter and Saturn likely formed closer to the Sun than they are now, then migrated outward as they exchanged momentum with the protoplanetary disk. Neptune may have formed closer to the Sun than Uranus, then migrated outward and past Uranus along the way, which would explain some of the differences between these two otherwise similar ice giants. This migration reshapes the entire solar system. As the giant planets moved, they scattered smaller objects, clearing certain regions and populating others. The Kuiper Belt, the region beyond Neptune containing Pluto and thousands of other icy bodies, may have been created by Neptune's outward migration, which swept up objects and deposited them in stable orbits beyond Neptune's reach. Some theories propose that Jupiter migrated inward toward the Sun, then reversed direction and migrated back outward, what's called the Grand Tack hypothesis. This inward then outward migration could explain why Mars is so small, Jupiter disrupted planet formation in Mars's region, and why the asteroid belt exists. Jupiter's migration stirred up the asteroids and prevented them from forming a planet. The solar system we see today isn't necessarily the solar system that formed 4.6 billion years ago. The planets have moved, reshaping the architecture of the entire system, scattering some objects, capturing others, creating the configuration we observe now through billions of years of slow gravitational evolution. Earth's moon may have formed from debris when a Mars-sized object called Theia collided with the early Earth about 4.5 billion years ago. This is called the Giant Impact Hypothesis, and it's the leading explanation for how Earth acquired such a large moon. The impact would have been catastrophic. Theia, perhaps 10 to 20% of Earth's mass, slammed into the young Earth at an oblique angle. The collision vaporized much of Theia and a large portion of Earth's mantle, creating a disk of debris orbiting Earth. This debris, a mix of vaporized rock from both Earth and Theia, gradually cooled and coalesced into the moon. Evidence for this hypothesis comes from several sources. The moon's composition is similar to Earth's mantle but different from other bodies in the solar system, suggesting it formed from terrestrial material. The moon has very little iron, consistent with being made mostly from mantle material rather than planetary cores, and isotopic analysis shows Earth and moon rocks have nearly identical compositions in certain elements, suggesting they share a common origin. The impact would have left Earth as a molten ball, its entire surface an ocean of magma glowing red hot. The newly formed moon orbited much closer than it does today, perhaps only 15,000 miles away, appearing enormous in the sky and raising tremendous tides in the molten rock. Our moon is made from pieces of Earth, flung into orbit by the most violent collision our planet ever experienced. We're looking at a part of Earth that was torn away and reformed into a separate world, locked in orbit around us for billions of years, a permanent reminder of ancient catastrophe. The planets will continue orbiting for billions of years, but eventually gravitational interactions could eject Mercury from the solar system or send it crashing into Venus or the Sun. The solar system's stability is not eternal. Computer simulations of the solar system's long-term future show that while most planetary orbits are stable for billions of years, Mercury's orbit is chaotic on timescales of 1 billion years or more. Small gravitational perturbations from the other planets accumulate unpredictably, and there's a small but real chance that Mercury's orbit will become highly eccentric. If Mercury's orbit becomes eccentric enough, and several fates are possible, Mercury could collide with Venus, it could collide with Earth, it could fall into the Sun, it could be ejected from the solar system entirely, sent wandering through interstellar space, or it could destabilize the orbits of the other inner planets, triggering a cascade of chaos that reshapes the entire inner solar system. The probability of any specific outcome is low, probably a few percent at most over the next 5 billion years, but it's not zero. The solar system's current configuration, which has persisted for about 4.5 billion years, is not guaranteed to last forever. Chaos theory tells us that tiny differences in initial conditions can lead to wildly different outcomes over long enough timescales. The solar system's future is genuinely uncertain, written in probabilities rather than certainties. We live in a solar system that appears stable, orderly, predictable. But over truly vast timescales, billions of years, that stability breaks down. The dance of planets will continue, but the choreography may change in ways we cannot predict, driven by the subtle accumulation of gravitational perturbations until perhaps something dramatic happens. The future of our cosmic neighborhood is uncertain, and perhaps that's fitting. And there we are. 100 facts about planets, these ancient worlds that have been spinning through the darkness since before Earth had continents, before the moon looked the way it does now, before the sun reached its current brightness. Planets are stranger than we often realize. They rust and shrink and spin backward. They have hexagonal storms and subsurface oceans and rings made of shattered moons. They migrate through the solar system, reshaping the architecture of worlds. Some are falling toward their stars, some are drifting away from their moons, some are doomed to be torn apart billions of years from now, and yet they endure. They've been orbiting for billions of years, and they'll continue for billions more, following paths carved by gravity, shaped by collisions that happened when the solar system was young, marked by processes we're still learning to understand. Perhaps that's the most remarkable thing. Not that the planets are strange, but that they persist. Through all the chaos of the early solar system, through all the collisions and migrations and catastrophes, they're still here. Still orbiting, still turning, still existing in configurations that have lasted longer than we can properly comprehend. Tonight, as you drift towards sleep, the planets are still out there. Jupiter is still spinning faster than any other world, its great red spot still churning. Saturn's rings are still catching sunlight, still slowly spiraling inward. Neptune's winds are still howling in the darkness at supersonic speeds, and Earth is still turning beneath you, carrying you through the night toward another sunrise, just as it has for billions of years. Sleep well, wanderer. The planets will still be there tomorrow, following their ancient paths, keeping their slow time waiting patiently in the darkness. Good night.